Thank you.
Okay.
There is no on, right? Okay.
Okay, good afternoon everyone. So let us start the afternoon session. So in this session the first talk is by Shubhodip Mukherjee from TIFR, and he will be talking on building the standard model of cosmology using gravitational waves.
Great, thanks a lot. So thanks a lot, Ananda, and for the introduction, and also the organizers for this nice timely meeting. I'm going to change the gear a little bit now, and you have heard excellent talks this morning on several electromagnetic probes to the universe, and which has helped us in building the standard model of cosmology. And as my title says, I'm going to tell you how gravitational wave observations are going to be particularly useful in this decades-long endeavor of getting our cosmology right. If I have to, okay, sorry. Yes. Okay, so long story short will be that this is the history of the universe that we have learned so far in using several electromagnetic observations, primarily driven by cosmic microwave background from high redshift, you heard this morning, and also from the low redshift universe using several galaxy surveys, supernova observations. Some of those will be told to you in the coming days. What's interesting is that this particular mapping, which has been done from several electromagnetic observational probes from gamma rays to radio, connecting multi-billion observational data to get to the lambda core dark matter universe, there is a growing tension of several problems. What you have seen is challenges or tensions are not just unknown, but it's just going to be there, whether you're talking about Hubble constant tension or sigma A tension. But forget about those, there are some tensions which are even much longer, which can be connected to how black holes are formed in the universe, how have black holes grown in the universe, how the universe was back at the high redshift, as you have already started hearing, that there are many more surprises which JWST observations is bringing to us. So this mapping is definitely a question now, where possibly at some places gravitational waves can make it as very simple, nice probe which is a better and deeper in some aspects than the other. So let's to understand how gravitational waves actually is a better and a deeper probe to the universe to understand the lambda core dark matter. So the good part is that we don't understand our standard model. So it's not yet on the book for us to say that we have understood everything. We have a more long list of things we have never understood. So a lot of work to be done. So that's a message for the students and postdocs. There are a lot of things to do to really make our standard model of cosmology stands in the field of data. And what really gravitational waves helps in bringing is that it's a probe which can go very deep. It can see the universe up to high redshift, thanks for its very weakly interacting property with foreground, so-called dust contaminations are not there, several advantages by which we can actually go to very high redshift. To be just, I'll not talk about this much, but I'm presuming there will be some talks at the end of in some part of this meeting, telling you about that you can actually go to the very early universe much deeper than what you can go with CMB, because there is no such thing as optical depth. I can really use stochastic gravitational wave background to go very deep in the universe. And thanks to a lot of engineering frontiers which has really helped us in getting to this particular scenario now, where you are able to measure gravitational wave in multiple bands. As like electromagnetic signal, gravitational wave comes in multiple spectrum from very low frequency which you can see from cosmic microwave background. Today morning Rishi and Tuhin talked about it, to the extent of a very high wavelength frequency, high frequency signal which is seen from LIGO Virgo Kangra and in near future from LIGO India, which are particularly coming from stellar origin binary black holes. And in between I have two more windows which are funded and operational. One is the nanohertz gravitational waves, good in seeing the supermassive binary black holes in the universe, and the millihertz gravitational waves, which are particularly excellent probe to see the millions to thousands of solar mass black holes. So what I plan today, that I definitely cannot cover a lot of aspects which we work on. I'm going to give you an overview on some of the interesting things. You already heard Harsh on non-gravitational aspect this morning. I'm going to particularly focus on the gravitational wave part, and I will tell you how the gravitational wave observations is something which is extremely fascinating, in my opinion, in these four regimes: length, redshift, source, time scale. You can see a source up to very high redshift, as I just now argued, with the help of ongoing and upcoming detectors, way up to a redshift of few tens to close to 100. I can see a single source which can be written in terms of first principle emission mechanism using general theory of relativity from a few seconds or milliseconds to time scale of years. I can see a source in LISA for years instead of which I see in LIGO for a few hundreds of milliseconds to a few seconds. These sources are of all different kinds, from binary neutron star to supermassive binary black holes. So you can possibly understand, I can measure a signal in phase up to very high redshift whose amplitude can be given from the first principle. And very interestingly, for all aspects I can explore physics from scales of a few kilometers when the black holes are very nearby, the scales of cosmological scales, because cosmic expansion history of the universe gets imprinted on the gravitational wave signal. And this really, what it brings to us is the way to map the entire expansion history of the universe in terms of very different kinds of sources. Instead of talking about cosmic microwave background like photons, or instead of talking about galaxy surveys, quasars, now we have a different tracer of the universe. It's a tracer, it's a binary black hole of all different masses. Binary neutron star and neutron star black hole systems using which you can go up to very high redshift universe, and as a result it naturally becomes a probe to cosmology. And can possibly answer several of your questions, and depending upon what is your interest, you can find your favorites. I am going to cover a little bit today on some of the parts which has been seen from the data as so far using LIGO for Kagra, and some aspects which will be opening up using nanohertz using SK observations. So at first I will talk about gravitational wave emissions from sources with EM counterpart and without EM counterpart. The one which is marked in the circle is the most promising one, most precise but fewer in number. And the other one is more in number, but each of them are not very precise. And we have seen about one of these and about hundreds of them. So these are the binary black holes. Why is it becoming an extremely important aspect to measure the expansion history of the universe, whether it's physics or systematics? So the way I put it, there is an ignorance of ours in either modeling cosmology or modeling astrophysics. There's a problem somewhere. And the long story short is that there are two inferences of Hubble constant from low redshift and high redshift probe. They don't agree with each other. I'm pretty sure this community don't need an introduction to this particular topic, but we can talk about this later during coffee in case you need some more clarification. But I'm going to talk about this our results on gravitational waves, which has provided weak but first measurements using multi-messenger signal using gravitational waves. So there exists two ways to measure it. If I can see the electromagnetic counterpart to the gravitational wave source, like a source having a neutron star or neutron star black hole, or a source without a black hole. And the way the technique works is that if I give you this bunch of stars, if I tell them like a gravitational wave source, they're not going to follow the underlying distribution randomly, but they're going to follow the distribution of the background structures. So these are the places where structures form, high density regions where I can expect to see galaxies and black holes, and as a result, I can possibly explore something called as clustering between gravitational wave sources and galaxies for those sources which has better sky localization error. So how this works? So I have to combine two different probes, I have to combine two different probes. In one side, I have a good distance tracer, which are the gravitational wave sources. And the other side, I have a good redshift tracer, which are like spectroscopic galaxies, such as DESI, and in very near future data will be available from SphereX and Euclid. As a result, one can do spatial clustering measurement of gravitational wave sources and galaxies to infer their clustering redshift. A very promising window, and this first application is done on GWTC3 for the very well localized gravitational wave sources. Sources for which we have sky localization error less than 30 square degrees, only 8 in number out of 90 of them, about 94 of them, so about 10%. This 10% will grow with LVK and in LIGO India. But right now, this is the measurement we have. It tells us that a weak but first measurement using gravitational wave sources by both GW170817, which is a bright siren, along with the constellation technique shown by both of them together in black. And these two are the measurements by Planck and Shoes which disagree. The idea is in little long run, I will not have time to talk about this, but we have shown that using this particular technique, we will be able to reach about the 2% measurement with about 300-ish gravitational wave sources in the era of LVK, and with LIGO India it will be even more powerful. What do we need? We need a good sky coverage survey in spectroscopically, and that is possible from DESI, Euclid, and partly from SphereX. Moving on, a very interesting aspect which is now coming up is measurement of dark energy equation state, and rather we have started seeing possible deviations from lambda in this particular sector thanks to observations from DESI. But how accurate and how reliable are these measurements? One of the particular thing to understand is that when you try to infer distance from an astrophysical source such as supernova, there is no standard model of astrophysics I can use to get the luminosity correctly. As a result, distance is a very difficult thing to measure. Instead of redshift, where I can use the spectra and measure the redshifts. Gravitational wave brings a way to do a calibration-free inference of distance. As a result, a calibration-free mapping of the expansion history of the universe. In third generation detectors with gravitational wave sources such as from Einstein telescope and cosmic explorer, this is my student Afroz, who has shown that how well we can measure the redshift evolution of dark energy equation of state as a function of redshift for a variety of model and different sources, which includes neutron star, black hole, and binary neutron stars. The main take home you have to remember is if there is a probe which I can go at different distance, measure its redshift, and make an inference of the h of z, it's a direct tracer of the expansion history. As a result, the dark energy equation of state reconstruction becomes a part of the story, but I can do a full reconstruction of h of z. And when you compare such results with other upcoming surveys, this is the error bars feasible from DESI, Euclid pessimistic, optimistic, W first baseline and extended, in comparison with what gravitational wave can bring to us in the future. It tells us that even the best measurement of dark energy from W first will be not as competitive as what we will be expecting from cosmic explorer and Einstein telescope, such as from sources with binary neutron star and neutron star black hole. Binary black holes are not that great because they are ultimately going to be limited by the errors we have in the galaxy surveys as well. But the main take home that you should possibly remember from this slide, that if you would like to write a standard model of cosmology where you have measured precisely dark energy equation of state, you would like to use a probe which is most calibration free and least susceptible to systematics. A way to get that is using gravitational wave signal. Another important part is about gravitational lensing of gravitational waves. Dark matter is one of the most dominant contributions in the universe which gravitates. And one of the things which you absolutely don't have any idea. There are several ways to measure dark matter, possibly by interaction with standard model, but it goes without saying it is an assumption. Without that assumption, I really do not know how dark is dark matter, but one thing I know, it gravitates. And a direct probe of gravitational effect of dark matter is through gravitational lensing. What really happens, thanks to the gravitational wave observations, is a very interesting thing. The largest wavelength of electromagnetic observation is in radio, which is of the few meters, is smaller than the smallest wavelength of gravitational wave, which is of the few hundreds of kilometers we see from LIGO. As a result, the structure of the universe that we can probe using gravitational waves is very different from than what we can probe from electromagnetic observation. We will probe what electromagnetic observations are probing, but we will probe even more by the effect of microlensing on top of the strong lensing effect. This particularly happens when wavelength of the gravitational wave is comparable to the Schwarzschild radius of the lens. And as a result, I start getting interference pattern on the gravitational wave, which is never happens for most of the EM observations. This brings a direct window to the substructures in the universe. It is Aniruddha who has shown it for the first time on what we have from the LIGO data. It is the first model independent chromatic or achromatic test. It is now published on GWTC3. These are all the events we have so far. He has found that one of the events shows a mild 2.9 sigma, discoveries are always the borderline. We found something like 2.9 sigma, we don't find very interesting. We went and do a parameter estimation of the lensing properties, and it shows that it's not very interesting right now. But possibly in the future, this avenue will tell us about the substructure and the population of micro lens or chromatic lensing signal from LIGO, and of course from CET. I have little only time left, maybe 2 more minutes. I will talk about one of the very important unknowns in the universe. At least when I always say this, that much bigger problem in the cosmology is not only about Hubble radiation or sigma 8, possibly the high redshift universe. I mean, we have seen black holes at high redshift universe using quasars, but we do not know how it has evolved and formed. So one of the really important aspects to understand is if I now put black hole masses as a function of cosmic time, I will observe by all these different windows from LIGO to PTA, how the things evolve in this particular plane, how things have grown in the universe. We should not forget that that's an important piece of information which should agree with our standard model of cosmology. Along these lines, there are some recent exciting results showing first inference of redshift dependent black hole mass spectrum. This is a work by Christos Karankasis. This was PhD work a couple of years back, where it is shown that as a function of cosmological redshift from LIGO Virgo Kagura, is there any signature of redshift evolution of the mass spectrum? It is not yet strong, because we have only 90 sources, and out of that about 43 of them are above SNR of 12. But we are getting to a scenario where soon we have few hundreds of sources. So the question about is the black hole's mass spectrum evolving in the stellar mass end, we have a answer to that. More interestingly, not only about posterior distributions, now we can start talking about formation channels. This again, of course, is a work which is first time showing the black hole phase space. See, don't think about just probability distribution of masses. Think about how mass, spin evolves as a function of redshift. When you think about stars, stellar physics, we do not talk about just probability distribution. We talk about HR diagram, an observable window of two quantities that gives me the trajectories of different formations. This is a scenario where you have, in terms of different direct observable quantities, we have constructed the phase space of binary black holes to show how different formational channels will show up, and if they form up to an extent very distinct region, and as a result it maps to a probability distribution of black holes in the universe for both astrophysical and primordial black hole. This table tells us for different color how can I assign probability of possible formation channel, and that there is always a degeneracy. You cannot break that at this point. Moving on to the supermassive black holes, so we have an open question in the area to understand how these black holes are forming, how heavy they form and how early they form. We have seen quasar observation from very high redshift, which tells us that okay, there is a black hole, and how they have really evolved we do not know. But long story short, the competition is between accretion or merger. How these things two are happening. If it is accreting, gravitational wave is not the a very huge signal in respect, rather no signal, almost no signal. But for merging, yes. So if black holes are merging from small structure to large structures, how many of them form how early in the universe? The work done by Mohit, so we will not talk about the details. It has gone through a lot of hydro simulations connecting with large scale structure distribution, showing you that in future with square kilometer array, these lines, and these are with the current pulsar turning array, we can make an inference of the genealogy of supermassive binary black holes, how fast they are growing and how massive they are. This tells me that these are the redshift evolution of the masses and its connection with the stellar mass. We will be able to make for the first time measurements as a function of redshift of black holes growth using a square kilometer array in the coming years. So interestingly, a completely unknown area where now we have almost 100% error bar, we will start getting measurement by basically asking, for in the nanohertz data, are we seeing more signal coming from high redshift or low redshift by seeing a synergy with LSST and SKA galaxy surveys. And by cross of these two quantities, we can get a measurement of its redshift evolution. I think I rushed about this part a bit more because I do not have much time. What I would like to tell you is that posing the cosmos with stellar gravures is just a new area now. In low redshift with individual objects, at high redshift with stochastic background, and this is just going to grow excellent with the upcoming already ongoing detectors and in future with LIGO India. And we should not forget about the synergy with several electromagnetic probes, where they will play an excellent role in what I call as the area of multi-messenger cosmology. With this, I will end my talk. Thank you so much.
So can you go to the slide where you had this evolution of W of Z? Now, there will be, just like in the case of supernovae, there will be significant astrophysical effects that will, this is ambitious, and there will be, similar astrophysical uncertainties, much like what you have in the case of supernovae and other electromagnetic counterparts. And in fact, it will be worse. So,
Okay.
I'm not convinced that.
Okay, so let's list down what we don't knows about supernovas and black holes. It is true that stars are complicated, but once stars aims into a black hole, thanks to GR, is just the mass and radii and spin. It doesn't matter much about what is the underlying property of the star that from which the black hole has formed. But the very fact that I see a gravitational wave signal in phase, its inspiral time scale and its amplitude, when I combine these two together, Bernard Schulz has shown back in 1986, I can get a direct measurement of the luminosity distance without doing any calibration on mass. But doesn't, I need a shift. So these are wave sources with literary counterpart.
That is where the
Main astrophysics comes.
your beam is so much, you can put so many things there.
Yes, no. So this is with binary neutron star, for which we see.
This is not with LIGO India or anything.
No.
We are talking about
Yeah. This is with the third generation reactors. LIGO India cannot do dark energy equation state.
you have the arc second.
But the electromagnetic counterpart will tell us the position and the sky localization.
Just to continue. No, I know, but this is what he meant by ambitious. Okay, so what I just following up with this, it's curiosity. Why nobody is worried about how to find out black hole merger by EM counterpart? You are already assuming that it is not a problem.
No, it
Means
is
you make the problem as a mathematical problem, right? Because you say that somehow some things are happening, I am not going to see, I will statistically detect. I am asking this question to a lot of people. This is such an important problem. You see, black hole exists in vacuum, only in paper, pen and paper, right?
That's right.
But in reality, it is surrounded by a lot of material, lot of
Exactly.
and there is something called gravitational influence.
Yes.
Each black hole has its influence and it collect all the garbage within that influence.
Yes.
So why can't it produce an electromagnetic signal?
No, it can. So
Why nobody is talking about it? You are going statistical.
No. So this one is not with statistical.
No, if you get that, you measure it up to redshift 6.
Yes, so I'll tell you something. So this avenue, basically what he's saying that what if black holes have material around them? Yes. And this is a very interesting avenue to look for black holes in the accretion disk. We have looked for this. We have an event called 190521, promising candidate but not a discovery. And we still look for it on the real data, but we haven't found anything so far. But for binary neutron star, we have a GW1717 light event, and this is for BNS. This is for neutron star. But if I do it for AGN,
I'm sure you got my point.
yes, but I got your point. What I want to tell you is that from LISA sources to a bit massive black holes in LIGO band or CET band,
If you go and look at some signatures of binary black hole in electromagnetic spectrum,
yes,
you will find them when they are at the kiloparsec scale.
yes,
It's not nothing to do with your
this case, yes. But that is in the most in the nanohertz we will see.
small fraction of those guys are going to do this. So you have
Yes.
to do little more work.
No,
Not from a simple thing. You have to do some work which is not trivial.
no, I agree. So this is not a trivial piece. The thing is that this piece comes from only neutron star part.
This I understand.
Yeah, not from black holes.
Hey, look, if you give me redshift and if somebody tells me what is the
Distance.
but this is a neutron star, I will do it. You don't have to do it. An astronomer will do it.
Yeah, I mean,
Not a problem.
no, but from black holes, those in the AGN disk.
I'm just
Yeah.
provocating you because you are saying
Okay.
so much you can do. That's the theory which is waiting for somebody to crack it.
Yeah, we are doing it now, but maybe a few more years are required.
Okay, so I think we can stop here and let's go. Let's again thank Shubhodip.
Thank
for
you.
his presentation. Next speaker is Orko Banerjee from ISAR Pune, and he will be talking about constraining cosmology beyond two-point function, nearest neighbor distribution and application to cosmological data. আমি 12 মিনিটের সময় বলবো 5 মিনিট।
This is fine. This is fine. I'll do it with the. I just need the pointer. Okay. So thanks to the organizers for this opportunity. So I will be talking about harnessing information from higher order statistics in cosmology. This has been touched on by quite a few speakers this morning. So I will present my own version called the K nearest neighbor distributions. This is work done in collaboration with a whole bunch of collaborators. So let's get started. So we are living through an era of rich cosmological data. Now that data can look like continuous maps. So maybe the Planck temperature field, weak lensing mass maps, or they can look like discrete objects. So these are the DESI galaxy, these are galaxies in DES. So this data comes in various formats, okay? And then following on from the last talk, this is the posterior from the BBH mergers in LIGO. So data can look like this as well. Now, what we want to do is we want to use this data to answer some of the fundamental questions in cosmology. So pick your favorite. Is it early universe, inflation? Is it late time expansion? Is it neutrino mass? Is it dark energy? So we want to answer each of these questions. And to do that, we need to be able to extract the most information that we can from the data. Now, over the last few years, we are getting better and better at predicting the gravitational collapse of a lambda CDM universe. Okay? So this is a simulation thanks to my student Vikhyat. So this is just looking at the density field evolution as a function of the neutrino mass. So this neutrino mass again is one of the things we have promised the community that we will deliver on. So we know how to run simulations deep into the nonlinear regime as a function of these quantities. But most of the analysis still uses the 2-point correlation function. So our favorite DAO peak, for example, is measured in the 2-point correlation function. Now the 2-point correlation function is the ultimate summary statistics for a Gaussian random field. So for the Planck map, or for very large scales even at low redshifts, the field is a Gaussian random field, and so the 2-point correlation function is enough for us to get the total information out of it. But as we saw from the previous simulation, on small scales the field is extremely non-Gaussian, and the power spectrum is not able to extract all the information there is. And ironically, cosmological surveys will provide exquisite data precisely in this regime. Okay? There is low sample variance on small scales, so that noise is low. And we will fail to fully utilize the power of these experiments if we do not look for techniques that can probe the non-Gaussian information. Okay? I'm not the first person to talk about this. This is an active area of research. You can broadly split it into two sort of techniques. One is called field level methods. I don't know if anyone is going to talk about it here. The other is through human interpretable higher order statistics. We've already heard in the morning about the bispectrum. We've also heard about the 1-point PDF. There are Minkowski functionals. We heard about the Mach power spectrum and so on. So this is a very active area of research. What I'm going to do is first give you a list of what we want from summary statistics that are looking to go beyond the Gaussian part. First, of course, they should capture as much information about the data distribution as possible. Secondly, it should be easy to apply to different kinds of data sets. You should be able to talk about autocorrelations in a data set, cross correlations between data sets. You should be able to apply it to continuous maps, discrete data sets, everything. Third one is that they should be computable in feasible time on the data and many instances of theoretical predictions, because for really nonlinear scales you can't get away from simulations, so this has to be quick to compute. We also probably want to understand the underlying theoretical connections between the various proposed summary statistics, This will help us understand which summary statistic is better at doing what, how to break parameter degeneracies, and also how to mitigate the effects of systematics and potential errors. Okay? With that, let me dive into a particular summary statistic that I have been developing over the last few years. This is called the k nearest neighbor distribution. So let me give you an illustration of how it works. So suppose my data lives in this square. Okay? First, what I will do is I will sample this with a dense set of query points. So these lightly colored points I'm going to call query points. The actual data points are these more solid points. Okay? What we do is, given this data, we go to every query point and ask how far away is my nearest neighbor data point. Okay? I can go to any query point and ask this question: how far is my first nearest neighbor, second nearest neighbor data, third nearest neighbor data, and so on. So at every point I will generate a list of k distances. I'll visit another query point and generate this list again. Now, let's say we look only at the nearest neighbor points from every query point. I can sort the distances, and that immediately gives me the cumulative distribution function of the nearest neighbor distances. So a single measurement is sufficient for a range of scale. So if I plot the CDF, I get the CDF as a function of scale. So this is the cumulative distribution function of the nearest neighbor data points, the second nearest neighbor data points, the third nearest neighbor data points, and so on. And the second thing, very crucially, is that this is extremely computationally inexpensive. This scales like n log n, so just like the 2-point correlation function. So this is super fast. This works on a few seconds on a single core. So this is what I am calling my summary statistics, the k nearest neighbor cumulative distribution function. Okay? Let me quickly give you a flavor of what it is measuring. So on the left and the right, I have equal numbers of points. On the right, I have just thrown the points randomly over this volume. On the left, they are actually gravitationally clustered. What is the first thing that strikes you? I would say the first thing that strikes you are these empty regions, which are the voids. So if a data set is clustered, compared to another data set with equal number of points but with the same number density, you will see larger gaps. So if I am a query point sitting here, my nearest neighbor data point is going to be far away. So my cumulative distribution function plateaus to 1 at a larger radius. Okay? So more the clustering, the CDF value changes differently. Okay? Okay, of course this is not quantitative. Quantitatively, we were able to write down the generating function for those k nearest neighbor distributions. So each nearest neighbor distribution is just a derivative of this generating function. The nice thing about the generating function is that it has a closed form expression in terms of these quantities I call xi of k. Now, these xi of k's actually correspond to integrals. So let me look at the k equal to 2 p's. The k equal to 2 p's is an integral of the 2-point function over all configurations that fit into a sphere of radius r. Okay? So this is one configuration that fits here. This is another configuration that fits there. So I can write the integral over all such configurations, and that is one of the terms here. The next term asks me to consider triangles instead of just pairs of points. I integrate over all such configurations. So this is actually an integral over the 3-point function. In this way, you can show that the generating function and therefore the CDFs are actually sensitive to all endpoint functions in the data. Okay? And we were able to show in a number of cases, both on data and on simulations, that we get much more signal to noise compared to the 2-point function because we are sensitive to all endpoint functions in the data. So this is one paper on actual data, which is the 1000 richest red mapper clusters in SDSS. But for example, in this study, using simulations, we were able to show that if you are interested in primordial non-Gaussianity, the fact that these nearest neighbor distributions are sensitive to all endpoint functions in the data helps you break degeneracies much better between primordial non-Gaussianity and halo parameters compared to even combining the power spectrum with the bispectrum. Okay, so 2 plus 3 point is still not as good as the KNN distributions. I want to spend a little time on this relatively new paper. So we have understood the k nearest neighbor distribution functions from the algebraic perspective of how they connect to the endpoint functions. In this paper led by my student Kwanit, we looked at the geometric interpretations of these nearest neighbor distributions. So given a set of data, if we ask at a particular search radius, where are all the query points that contribute to the value of the cumulative distribution function at that r? They will form these spheres around the data point. Some of them will intersect depending on the radius that you are interested in. So the value of the CDF is actually directly proportional to the volume contained in these spheres. Okay? So the CDF is simply proportional to the volume that you see on the figure. But now I can ask, at this particular r, how is my cumulative distribution function changing, or what is its first derivative, let's say. So that question can be reframed as asking, where are the query points that contribute to the change in the volume at that radius? And where are they? They are lying on the surfaces of these spheres. These are the outer intersections of these spheres. Again, I have a clear geometric interpretation of what the first derivative of the CDF at a particular point corresponds to. I can then ask, what does the second derivative correspond to? It turns out with some mathematics, you can show that the second derivative corresponds to these red areas, which are the angles of the intersections of spheres. Okay? There's a trivial piece which comes from the outer shape. Okay, so the second derivative of the CDF tells me the angles at which these spheres are intersecting. And finally, the third derivative of these cumulative distribution functions actually are directly related to what are called the Euler characteristic. So you have those unions of spheres. The third derivative of the CDF can be directly used to calculate the Euler characteristic of this complicated shape. So this was a neat sort of a conclusion. We were able to show that the first nearest neighbor CDF and its derivative have intuitive and beautiful geometrical or topological interpretations. And funnily enough, they are exactly equal to what are known as the Minkowski functionals in the literature. So the Minkowski functionals are the volume, the surface, the integral, mean curvature, and the Euler characteristic for a set of intersecting spheres. They don't have to be spheres, but anyway. However, all the Minkowski connections are to the 1NN CDF. You can give geometrical interpretations to the higher order CDFs as well, and the information in the higher KNN CDFs is beyond the traditional Minkowski functionals. So now we have tied it in, neatly both from the algebraic perspective of the endpoint functions and the geometrical or the Minkowski functional picture. So is that all that we can do with these statistics? The answer is no. We can also generalize these statistics to take into account cross correlations. I'll go over this a little more quickly because I have 5 more minutes. But what we have been able to do is generalize what I had shown you about the auto clustering of a set of points to talk about cross correlations. And again, in the cross correlations, we were able to write down the generating function in a closed form, and again show that these are related to terms that are integrals of the 2-point correlation function. But now since there are 2 types of data, one is red and one is blue, let's say, this is the integral over all configurations of 2 red points, 1 red, 1 blue, 2 blues. Then there is another term that are integrals over triangles of 3 reds, 1 blue, 2 red, 2 blue, 1 red, 3 blues, and so on. So if you measure cross correlations using this formalism, you are not only measuring what is called the Gaussian cross correlation between 2 data sets, but all possible correlations. So if you don't find correlations, this is called statistical independence. We also generalize the formalism to not only think about discrete data like red galaxies and blue galaxies, but cross correlations between one discrete data set and one continuous map. Okay, so for example, galaxies and 21 centimeter maps. What are some of the applications? So this is work led by my student Ishika, where she showed that if you're looking at cross correlations between, say, a chime-like experiment and a galaxy survey, if you use our cross correlation technique, which is on the right, compared to the 2-point function, sorry, my mistake. If you compare the signal to noise in the 2-point correlation function, which is here, the chi-square of the data lies within the null distribution. In other words, you get a very weak measurement of the cross correlation signal between chime and galaxies. If you use the nearest neighbor cross correlation method, this is the chi-square that you get. This is, I don't know, 10 sigma detection. Similarly, you can play around with the amount of time you integrate in chime, the noise, the foreground cleaning, and in every case, you get much stronger detection of the cross correlation signal if you use these nearest neighbor way of measuring correlations. Other applications, so this is work led by Kaustubh, who was my master student, and this goes back to what Shubhadeep was talking about. You might be interested in the dark siren method, but the dark siren method actually relies on measuring cross correlation between a galaxy sample and the BBH events. What we showed was that no matter what statistical significance threshold you set, suppose I want to detect at 5 sigma, the clustering signal, you will get there with far fewer events if you use the k nearest neighbor way of cross correlations compared to the 2-point that most people are using right now. Similarly, you might be interested in cross correlating high energy neutrino sources in IceCube with a galaxy sample, because we don't know exactly what sorts of galaxies or what sorts of events in these galaxies lead to these high energy neutrino emissions. Again, you would need far fewer sources to get a measurement of the cross correlation. So basically it's taking, cross correlations between things that look like this and things that look like that. Okay. Before I wrap up, you can also take the actual map. So this is the same data represented on the left and the right, except on the right, for every pixel, I have simply colored it by the distance to the nearest neighbor. Okay. And you can clearly see a nice pattern. This is actually the Voronoi tessellation of this picture. What I'm doing with Othrideb, who was a postdoc at IUCA and has now moved to Groningen, is to see if with machine learning, we can extract even more information out of this raw image compared to the information that we already capture in the distribution functions. Okay. We have some preliminary results, but I will not waste your time here. We can discuss this over coffee if you are interested. So let me summarize. So the k nearest neighbor measurements offer a new way of measuring cosmological clustering of nonlinear fields, both auto and cross correlations, and both continuous and discrete data. These are computationally extremely cheap. These scale just like the 2-point correlation function, yet they are sensitive to all endpoint functions in the data. There are analytic connections to higher order statistics, higher order endpoint functions. There are also really nice connections, geometric connections to the Minkowski functionals and other topological quantities. I didn't talk about it, but these nearest neighbor distributions can actually be well modeled on mildly nonlinear scales using this thing called the hybrid Lagrangian bias approach. On small scales, we have modeled it using an HOD framework. So we've also worked on the modeling part. If you're interested, we can talk about it. In the last couple of minutes, I want to show you our new website. So all my students got together, put together all of our code. And now if you're interested in these statistics and using them, you can simply go to this new website. It has example data sets, calculations, how to use it, and everything put together. So let me just see if it works. So this is our website. It's called KNNPy. It links to the actual GitHub repo where the codes are. There are also installation and user guides. There's also a list of all papers that we have put together on this. So if you're interested in what sorts of science questions you can address with this, take a look. And yeah, I just encourage you to download it and play around with it and see if you find anything interesting. And with that, I will stop and take questions.
Thank you for very nice talk. So how do you propagate the observational systematics into when you calculate K and N, for example, masking or magnitude cuts and other things?
Very good. So masking, for example, we take into account by using a set of randoms. Usually all these surveys will have a set of randoms, and we look for the signal over and above what we get by throwing the query points with the mask included.
But then you will also have the interpretation of the first derivative a bit arbitrary near the masks.
Absolutely, yeah. That is absolutely true. So we often have to use a cutout region slightly larger than the mask to make sure that everything is robust.
Thank you.
Yeah, very nice work. So you talked about the link to the Minkowski functionals, and you made a statement that these are they can get more information out compared to Minkowski functionals. So how does that happen?
Yeah, so suppose you focus on a certain range of scales, right? Now, at the lowest R min, for example, some of those spheres have already intersected, let's say. So your Minkowski functionals actually start evaluating from that point on. So it doesn't have information of what has intersected before your R min of your analysis. But the higher end KN and CDFs actually can see the, let me see, might be here. So you can see that the higher KN and CDFs at a particular R are sensitive to what has intersected already. So that is how we get more information.
Okay. Then you stopped at the third derivative when you are making this. Can you not go higher derivative? Is there more information?
No, it stops there. We couldn't find a natural interpretation of higher derivatives actually. But you can also show that if you are in 3 dimensions, every intersection that new intersection that you have, all the information is captured within the first 3 derivatives. So just like there cannot be more than 4 Minkowski functionals in 3D, we seem to have a similar sort of interpretation here.
Okay, thanks.
So just following on the Prakash question, so how do you deal with the foreground contaminations?
Yeah, so in the study with Ishika, what we did, Ishika and Simon and so on, what we did was the easiest way is to cut on K parallel. So we threw out the wedge.
Okay.
But as one of the talks mentioned in the morning, we could also try to model it slightly better. That is to be seen. We haven't really gone into details.
Okay, thank you.
Okay, so thanks Orko again. And, the next talk is by Shobhik Roy Chaudhary. He is from Asia, Taipei. And he will be talking on cosmology in an extended parameter space, new constant on dark energy and neutrino masses with DESI bow.
Hi everyone, thanks to the organizers for giving me this opportunity to present my work here. So, so my talk will be based on these 2 papers. One was written with Teppei Okumura and the other one is single author. Both of them are published in the Astrophysical Journal Letters. So this work is on cosmology in an extended parameter space which has basically 12 parameters. Now, DESI showed preference for dynamical dark energy at the level of around, currently it's 2.8 to 4.2 sigma, depending on the supernovae data set used. But even without that, DESI plus CMB alone shows a 3.1 sigma preference for dynamical dark energy in the CPL parameterization. So in DESI DR2 paper, the data release 2 paper, they see a phantom crossing happening for a multitude of parameterizations for dynamical dark energy using 2 parameters. Now, this uses total 8 parameters basically, 6 parameters for lambda CDM and then 2 for dynamical dark energy. Now, DESI also has a very strong constraint on the sum of neutrino masses in lambda CDM, which prompted people to talk about negative neutrino masses or maybe neutrino decay, which is masking the effect of neutrino masses. Because if you extend this posterior, it will actually peak in the negative neutrino masses. So, and it's also even challenging the normal hierarchy, which requires 0.06 eV of minimum neutrino masses. So the bounds do relax with dynamical dark energy, but still we do not see a peak in the posterior in the positive neutrino mass direction. So in our paper, what we did is we used a 12 parameter model. So we have the first 6 lambda CDM parameters, then W0, WA for dynamical dark energy, then simple extensions, an effective or number of effective number of neutrino species, sum of neutrino masses, then running of the scalar spectral index, and ALens, which is a artificial scaling of the lensing amplitude. These are simple extensions, and so the power spectrum basically has AS, NS, and this extra alpha S parameter, which is the scaling of the spectral index basically. And we also use CPL for dynamical dark energy. Now, our main goals are to check for the preference of dynamical dark energy in this extended parameter space, if it survives or not. We want to provide a reasonable bound on the sum of neutrino masses by, we want to provide a robust bound because the parameters we choose like W0, WA, and ALens, they are correlated with sum of neutrino masses, and that will change the bound, and we want to see if we can see some evidence for positive neutrino masses. We want to give a definitive answer to the lensing anomaly case, which was there with the Planck PR3 likelihoods, but it's not present in the Planck PR4 likelihoods, but in lambda CDM model. Nobody has checked it for dynamical dark energy. Now, lensing anomaly is a case where the data prefers more lensing than that is theoretically expected. So the ALens value should be equal to 1, and if it deviates by more than 2 sigma from 1, then we have a lensing anomaly. We also want to assess the level of the Hubble discrepancy in our 12 parameter extended cosmological model. So how far we can decrease the tension from currently, the tension is at 5 sigma, so we want to see how much we can decrease it. So we use Planck public release 4 likelihoods for high L temperature and polarization along with low L polarization data. And we use the commander likelihood for Planck 2018 low L temperature data. For lensing, we again use the latest Planck PR4 and Atacama Cosmology Telescope data release 6 lensing likelihoods. For BAO, in the first paper we had data release 1 of DESI, and in the second paper we have data release 2 of DESI. For supernovae, we use Pantheon Plus and DES year 5 separately, and so these two have some supernovae which are common, so you can't use both of them together. So you can't use Pantheon Plus and DES year 5 together, because then there will be some double counting issues. For weak lensing data, we use dark energy survey year 1 data. So one of our main results is that when you go to a 12 parameter space, then with Pantheon plus along with CMB plus BAO, these red contours, 1 sigma and 2 sigma red contours. What we see is that the cosmological constant is at the edge of the 2 sigma range, and for DES year 5 it is excluded at more than 2 sigma. So the evidence for dynamical dark energy in this 12 parameter model is basically inconclusive and data set dependent. And with Pantheon plus we still have a part of, so this parameter space is for quintessence, and quintessence where the equation of state doesn't go below -1. So some parameter space is still allowed with Pantheon plus, but not with the ACR5 basically. So this is a relatively important result because DESI's claim is much stronger, but simple extensions to their model can actually reduce the tension to a large extent and allow cosmological constant at least at the boundary of 2 sigma contours. For neutrino masses, when we use only CMB plus BAO plus supernovae, what we see is that CMB plus BAO gives us a peak in the positive mass range, and same with CMB plus BAO plus DES5, but Pantheon plus doesn't give a peak basically in the positive mass range. But after we use the weak lensing data, there is a strong correlation with S8 and some of neutrino masses, and that makes the peaks much better, and we actually have the first 2 sigma detection of some of neutrino masses of around 0.19 plus 0.15 minus 0.1 ETV with this CMB plus BO plus DSER5 plus the DSER1 weak lensing data. So this detection is at 2.1 sigma level, and with Pantheon plus we get a detection of at the level of 1.9 sigma. So yeah, this is quite a big result in this paper. For lensing anomaly, we have some interesting result that so with CMB plus BO plus supernova, it is okay with A lens equal to 1 at less than 2 sigma. So, but when we use weak lensing data, the smaller S8 values of weak lensing make the lensing anomaly much worse, and it's actually a more than 2 sigma tension when we have the weak lensing data. So these plots basically. So as you can see, the supernovae data have produced similar values of A lens, but when we use weak lensing, the result changes. So yeah, okay. So this is again for the first time we show that the existence of the lensing we show the existence of lensing anomaly can depend on non-CMB data sets. So previously this lensing anomaly was associated with Planck 2018 likelihoods or Planck PR3 likelihoods, and Planck PR4 likelihoods did not show any existence of lensing anomaly in the lambda CDM model, but in a dynamical dark energy model you can find the evidence of lensing anomaly with weak lensing data. In case of Hubble tension, in the first paper we found that the tension persists around 3.2 to 3.9 sigma with CMB plus BO plus supernovae. In the plots you can see that these are Planck plus lensing, and they don't, so Planck, CMB is not sensitive to H0 that much because H0 is very much correlated with these W0, WA parameters, and with addition of BAO you get some constraints, and for proper constraints you do need the supernovae data because when you constrain W0, WA with supernovae, then only you can get a proper constraint on H0, and then Hubble tension persists at the level of 3.2 to 3.9 sigma in the DESI DR1 case, but in the DR2 case we find it's a bit larger at 3.6 to 4.2 sigma depending on the supernova data set used. So you can say that the Hubble tension is quite robust, and you need actually much more non-trivial extensions to lambda CDM to solve Hubble tension. These simple extensions are not enough. For the S8 tension, we find that with DES year 3 weak lensing data, it is reduced to 1.4 sigma with CMB plus BAO plus supernovae. So the main effect seems to be coming from Planck PR4 likelihoods instead of Planck PR3, because with Planck PR3 the tension was more than 2 sigma. So S8 tension is not to be considered strong tension anymore in cosmology. Basically, with the new kids results, that has become even more apparent that the S8 tension is not a big tension anymore. So these are some. These are a few degeneracies of sum of neutrino masses which are important. Out of them, these three, with WA, ALNs, and S8, these are very important because weak lensing data prefers slightly lower values of S8, and that chooses slightly higher values of sum of neutrino masses. At the same time, it also chooses slightly higher values of ALNs as well. So overall, you can see from these correlation plots that how the results come about, basically, especially the detection of neutrino masses because of the small S8 tension, which is not a big tension anymore. That is why we can combine the data sets together, basically. So to summarize, CMB plus BO plus Pantheon plus allows for a cosmological constant at the edge of the 95% contour. So the evidence for dynamical dark energy component is data set dependent and not conclusive yet. We find the first 2 sigma detection of non-zero positive neutrino mass sum, and the peaks in the sum of neutrino posteriors indicate that in future we might find a 5 sigma detection as well. We recommend this bound for the particle physics and cosmology communities to use as reference. For lensing anomaly, we find that even with Planck VR4 likelihoods, we find the existence of lensing anomaly could depend on non-CMB data sets, and simple extensions to lambda CDM explored in this study are not enough to solve the Hubble tension. And lastly, the S8 tension with DESI 3 is reduced to 1.4 sigma. Yeah, thank you.
Two questions. One is something that you already touched on. You are in principle combining data sets that are maybe in tension. Let's say CMB and DESI. You are combining them in the model rather than checking if the extended model with just CMB allows you the DESI parameter space. Why is that? And second, I'll ask the question, you can answer. The neutrino mass being negative in DESI alone is simply a measurement of omega matter at late times being slightly lower than what CMB prefers. Do you understand why it shifts in your analysis? Is it AS absorbing most of it, or is it S8 absorbing most of it?
Okay, so to answer the first question, in the CPL parametrization, that omega m tension doesn't actually occur, that occurs in the lambda CDM model. So in lambda CDM, BAO prefers lower omega m, and the tension is at the level of 2 sigma as far as I understand with CMB data. But when you allow for W0 WA, then this omega m tension goes away. It's much less than 2 sigma, so it's not an issue to analyze CMB plus BAO together. Also, supernovae data actually prefers slightly higher omega m. So if you just combine Planck with supernovae data, you will get even a 3 sigma detection if you don't take BAO data at all. In lambda CDM model, you don't have to consider even dynamical dark energy. So it's important to note that the detection happens with BAO data, which is a new thing because people haven't seen it before. Now the second thing is that, as I said, there is a large negative correlation between S8 and sum of neutrino masses, and as it happens, weak lensing actually prefers lowers S8, but the tension is at the level of 1 sigma with DES year 1 weak lensing data. And if you consider this 12 parameter model, then calculate S8 from CMB plus BO plus supernovae, and then calculate S8 from weak lensing data, the tension is at the level of 1 sigma. So there is no problem combining them together. So in that sense, this is a detection where we have used data sets which are compatible with each other in this particular model. Of course, in lambda CDM, there might be problems, but not in this model at least.
About the A-lens parameter, which characterizes the strength of lensing just based on 2-point correlation. The ACT and SPT data over the years have shown that A-lens is consistent with 1.
Yeah.
So have you considered looking at it?
I have not used ACT or SPT data. What we have used is the Planck PR4 likelihoods, which also don't show any lens anomaly in the in lambda CDM basically. So in this case, we see an lens tension above 2 sigma with the weak lensing data, but not without the weak lensing data. So it's again happening because of this correlation. So S8 and sum of neutron masses are correlated, and A-lens and sum of neutron masses are also strongly correlated. So lower values of S8 chooses higher values of sum of neutron masses as well as higher values of A-lens basically.
Thank you.
Hi, yeah, just a quick question on the similar lines. So one of them is already taken regarding A-lens, that when you combine ACT and SPT, when you combine ACT and SPT, A-lens is consistent with 1.
Yeah, only with in lambda CDM usually.
No. So the A-lens, the problem is usually happening coming from the CMB TT with only a few multiples localized around 1400 values of L.
Okay.
Multiples, but my main question still remains is that when you're talking about kids data set, the photo-Z errors in the bins of the lensing, there is a uncertainty in the measurement of the redshifts of those window functions. And that's a possible way where the sigma 8, S8 tension may be already coming from. So how do you understand the possible systematics in different data set is not driving your neutrino mass to a positive value?
Here we are not using kids for that instance. We are using dark energy survey.
Kids have shown this, that they have a problem. DES have not shown this. That's one of the things we compare with. But kids have shown that depending upon the photo-Z bins, that window function, your SI changes. But I want to understand that how do you know that this is not sourcing you a systematic error? So the main problem is the amount of clustering seen in BO measurements and DES is different from what is seen in Planck or what Planck can say.
Okay, so here we are combining CMB plus BO plus supernovae first, and then checking it with weak lensing data. So weak lensing has slightly lower S8, but the two measurements are compatible with each other at the level of 1 sigma. So there might be systematics in DES, and as I said, the lower S8 values are driving the detection of sum of neutron masses here. So if there are systematic issues that they have to deal with, because I take them as on face value basically. Yeah.
Okay, so let's thank Shobik again. Let's move on to the next talk. It's by Shahnaz Yanadil. So he is from Unam, Mexico, and he will be talking on DESI and its implication for dark energy theories. Okay.
Okay, sir. Okay, sir. Okay, thank you, Anjan sir, for the introduction, and Professor Dheeraj and the organizers for having me in this conference. I will be talking about DESI and its implications for dark energy theories, and some of the slides may be repetitive from the earlier talks. So this is the first DESI result, which talks about the posteriors in the omega A and omega naught plane. And I will talk about that why this omega A and omega naught plane is important to define the dynamics of the dark energy. So when we combine only two observations, for example, only DESI BO and only DESI and DESI and supernova. So for the case of DESI and the DESI Pantheon plus, the lambda CDM point is between 1 and 2 sigma, but when we consider the union 3 and DESI 5 observation, this is beyond 2 sigma. But when we combine all these 3 observations, DESI, CMB and supernova, the discrepancy goes away from the 2 sigma regime. So for example, in the case of Pantheon plus, it is around 2.8 or something, and in the case of union 3 and DESI 5, it's beyond 3 sigma regime. So this is one such result, and this result can be systematically oriented or maybe theoretical inaccuracies. So when we talk about the systematics in the Pantheon plus observation, and we have this intrinsic parameter of this Pantheon plus, which is the absolute magnitude. So when we consider 2 anchors, for example, the early universe Planck and the late universe Schulze, so we see that there is a discrepancy of more than 2 sigma in the absolute magnitude parameter. So this is a systematic error in the Pantheon plus measurement. Also, when we consider the GRB data, again if we consider 2 anchors, for example the Planck and the Schulze anchor, so again we see that there is a discrepancy of more than 2 sigma in the intrinsic parameters of the GRB observation. So this is about the systematics. Again, if we bin the Pantheon sample in different redshift bins, so if we set some minimum redshift or if we set some maximum redshift in the sample of Pantheon plus, which is 1701. So when we consider the minimum redshift to be around from 0.0 to 0. Let's say 15, then we see that they are consistent with omega m value. But when we go beyond that cutoff, we see that the omega m is running, and a similar thing we see if we set a maximum redshift. So this could be attributed to the number of samples we have in the higher redshift regime. For example, if we go, so if in 1701 samples of Pantheon plus, if we go beyond let's say 0.5 or 0.7 redshift, the number of sample is quite small, which is around 100, and most of the samples are below these values. So maybe that is the reason we see this running of this omega m. So in the paper, Malik Jani et al., they thought about this idea, and they were using this actual data of Pantheon plus. They considered some different polynomials of this function, luminosity distance, and they fitted this model with different polynomial curves. So what they found that the most fitting curve is this function, the cubic power of redshift, and using this polynomial, they extended the number of samples for a higher redshift regime, and they created some mock data using this curve and this error bars of these observational data. So what they have found that if we equally divide the number of samples for less than 1 redshift and greater than 1 redshift, so again we see that there is a discrepancy between these 2 redshift, and they considered up to 10,000 samples of supernova. Maybe if they consider more samples, then they can, because we see that this is the behavior is going down, so maybe there is a consistency if we go beyond that 10,000 number of samples. So this is about the systematics, and similar thing we see in the RSD measurements of this S8 parameter. Again, we consider some redshift bins, we see the running in this S8 parameter. So again, as Sharik was talking about this negative neutrino masses, so in the new DESI paper, when from CMB alone, if they set priors on this, some of the neutrinos mass is free, so we see that the peaks are not in the positive but in the negative neutrino masses. And if we combine all those DR2 and CMB baseline observation, So the error bars have reduced, but again the peak is around minus 0.11. So again, if we plot this volumetric distance with lambda CDM, and we try to fit this graph with different sum of neutrino masses, so we see that the most justified line is with this negative neutrino masses. So, and this is considering the background lambda CDM model. So, as Sharik shown some interesting result that if we consider some dynamical dark energy, we can shift these peak to the right side, and that would be a very interesting result. Again, further, if we free this parameter, so there is a direct correlation of this sum of the neutrino masses with the H naught. So again, in context of Hubble tension, if we want to increase the value of Hubble, then we have to consider this negative neutrino masses in lambda CDM regime. And again, if we put this negative neutrino masses around this value, it perfectly fits this DESI Biot band. So this is the neutrino problem that we have with lambda CDM model. And so these are the problems in the lambda CDM. So that's why we need to look beyond the lambda CDM. And again, in the DESI paper, Loda et al. Paper, they reconstructed different cosmological parameters using these Biot data, and they found that this is equation of state. This is not a constant, but it has a dynamical nature with different combination of data sets. And this is the energy density fraction, again, which is not a constant, but it is it has some dynamical behavior. And this feature I want to focus on this feature because in most of the recent works we have found these features in the dynamical dark energy models. And this is the residual with compared to the lambda CDM model, and we see that for high redshift the lambda CDM and all those DESI dynamical dark energy thing, they are almost similar. So all those dynamical thing is affected in this 0 to around 1.5 redshift regime. So that's how we need to look beyond the dynamical dark energy models. And how can we do that? So when we interpret those data, so we have to have in dynamical dark energy models, we have to have the dark energy must evolve, super evolve faster than the Hubble friction after the matter domination. And dark energy should cross this -1 line, which is the phantom divide, and recently it has deviated away from lambda CDM. So how can we do that? So these are the two classes of dark energy that we have. One is the thawing one and the freezing one, and these are different regions. So in these regions, some of the standard principle have to be violated to lie the dark energy in these regions. And these are some dynamical. These are some dark energy models that comes under these thawing and freezing scenarios. So we have these 4 regions. One is this high region, middle region, low region, and there is phantom region. And the observation suggests that the dark energy is lying in this high region. So we can go from this W prime to W region to W naught WA plane. When we consider W prime to be minus WA, so when we take the Taylor expansion in first order, and then we put W prime to be W minus WA, and then we have this W naught as the first the ground value. So we see that in the most in the DESI paper we are getting this regime below this regime, and what are and we see that this WA and W naught plane justifies the dynamical behavior of the dark energy. So instead of taking the Taylor expansion of the equation of state, because most of the cosmological parameters are related with equation of state indirectly, they have first order integral or second order integral with the equation of state. We can directly expand the dark energy around the cosmological constant, and we can take the Taylor expansion of this dark energy, and it can have, depending on the model parameters, it can have different features. So we use this expansion, and then we get a very compelling evidence for this dynamical dark energy, and we see that for 3 extra degrees of freedom we have this is around 99% confidence level, and this is beyond 99% confidence level. We are getting the evidence of this dynamical dark energy, and when we reconstruct the energy density, we see that this is the feature that we are getting, which we see in the DESI paper. And lastly, this is the Hubble plot that we see, and we see that the DESI BO data point and the SDSS BO data point are justified by this model. So with this, I will conclude my talk that the impact of dark energy on observation is superbly accounted for in the W0 WA plane, and then we have certain zones of avoidance, and instead of taking the W Taylor expansion, we can take the dark energy expansion directly, and in the upcoming observations we will have those tight constraints on these cosmological parameters, and in the stage 4 stage 5 DESI observations, we will have 10 to the power 8 number of observation, and then we can get a more tighter constraint, and then we can talk about these different dark energy models. Thank you.
Talk in this session is by Yashi Tiwari. So she's from ISC Bangalore, and she will be talking on dynamical dark energy in the light of tension and standard cosmology.
Hello, yeah. Okay. Hello everyone, I am Yashi, I am from IC Bangalore. I'll thank the organizers to give this opportunity to present about my work. So this is a brief outline of my talk. I'll be talking about what are the emerging challenges to the standard model of cosmology, which is the lambda cold dark matter model. And with this, I will motivate for looking for extensions of the standard model, and that too in a modified gravity framework. Particularly, I would be talking about a scalar tensor theory, which is a generalized scalar tensor theory called Hondeski gravity. Following this, I will discuss my recent works during my PhD, which I have carried out in the framework of Hondeski gravity. And with this, I will conclude. So, yeah, we have a standard model of cosmology which is based on general relativity and cosmological principle, and which very nicely explains a broad range of cosmological observations. And this is a 6-parameter models which is built on 3 crucial ingredients: dark matter, dark energy which is a cosmological constant, and inflation. However, as is also discussed in many of the talks from morning, that there are some emerging challenges to this standard model, often referred to as the tensions and anomalies in standard cosmology. So at the forefront of these is the Hubble tension, which is a discrepancy in the measurement of H0 arising from 2 observations. Mainly the 2 observations which are in strong discrepancy is the one SHOES, which uses the distance ladder techniques to get an estimate of H0, and the other one is the CMB based measurements, which are based on assuming a standard model of cosmology, which is taken to be lambda cold dark matter model. Once you take the model and use the CMB data, you get an estimate of H0, which is on a lower side. So to illustrate, if you plot the PDF distribution of an observable H0 with the mean values from the two observations and their error bars, you see that they don't overlap, in the posterior distribution. And to illustrate better, if you plot the difference of the observables with their mean values, the difference of the mean values and their sigma, you see that the mean value peaks around 5 sigma away from 0, indicating the strong discrepancy between the observations. Now there have been various resolutions models proposed to resolve the Hubble tension. So they could be categorized into two parts. First is modifying the early universe, and the other is modifying the late universe. The idea is that if you are proposing any model which is alternate to the lambda-CDM model, the fit to the CMB should not be disturbed, because CMB is very nicely explained by the lambda-CDM model. So, and what parameter of the CMB is actually most sensitive to the dark energy physics is this angular size of the sound horizon, which is very precisely measured by the CMB observation. And this is a ratio of the sound horizon at the baryon drag, sound horizon at the time of recombination to the distance to the last scattering surface. Now, the resolutions that are based on modifying the early universe actually reduce the sound horizon, and which in turn leads to a large value of H0. However, there have been studies which have told that such type of modifications alone are not sufficient to fully resolve the tension, and thereby there is the other option, which is modifying the late universe, which is again tricky. The idea is that you need a faster expansion at late times to explain a large value of H0, which leads to a phantom type of behavior in equation of state, where the equation of state is less than -1, and this leads to a faster expansion. However, simple models like trivial phantom equation of state again is not favored by the data, because it alters the distance to the last scattering surface and thereby disturbs the peaks of the CMB. So there have been various studies which are based on parameterizations of equation of state and reconstruction of the dark energy properties from low redshift data, and these have indicated that the models where you have certain non-trivial features like phantom crossing, where there is a crossing in the equation of state of dark energy between non-phantom and phantom regimes, or if there is a negative dark energy at high redshift, or if there is a variation in the G effective, the effective gravitational constants, these features can help reconcile the data better in comparison to the standard model and resolve a lot of tensions. The point here is that all these non-trivial features actually cannot be realized in a general relativity framework, because they will lead to certain instabilities, and therefore there is the need to go beyond general relativity, which is one of the core principles of the lambda-CDM model, to realize these features and build the models. So this is the motivation for exploring the modified gravity theories. So there are certain other challenges, as already talked about, particularly the DESI. So DESI has found hints of dynamical nature of dark energy, but interestingly what is also there is that in the W0 WA plane, or even if the reconstruction of the equation of state from the data, there are hints that there could be phantom crossing at high redshifts. That is, the equation of state of the dark energy goes in the phantom regime at high redshifts. If this is so, if this feature persists in the data, then one needs to think of what type of model could actually lead to such type of phantom crossing, which cannot be realized in a general relativity framework. Similarly, there is a study which found that when you set the growth index parameter free, even on the top of a lambda-CDM background, there have been indications of suppression of growth rates. So using the data of the galaxy clustering and peculiar velocities, one can get an idea of the growth rate, how the growth rate of the universe evolve with the redshift with time. And even if at the background level the dynamics is very similar to GR, you can have differentiable effects at the level of the perturbations, where you can see in the observables like growth rate. So this recent study has indicated that there is this indication of suppression of the growth rate at the very low redshifts. So all these things are indicating that maybe there is a possibility of looking for extensions beyond general relativity, and that is what is the motivation that I have explored in my first work. So we are trying to see that whether we can derive these non-trivial features like phantom crossing or negative energy density at high redshifts by a Lagrangian, by introducing some scalar field interactions rather than working with parameterizations, and can we do so in a theory which is free of any instabilities like ghost or gradient instabilities, and can we also address the Hubble tension. So this is one particular framework, which is the Hondeski theory. It is a generalized scalar tensor theory of gravity. So it's a theory where the Lagrangian is constructed from metric tensor and a scalar field, including all sorts of possible contribution between the scalar field and metric. The point is the equation of motion always remains second order. So this was, this Lagrangian was constructed by Hondeski, who was a student of Lovelock. This was his grad project, and now he is a famous painter. And these equations are actually interesting because they can accommodate a large number of modified gravity theories together. For example, you can work with Galileans, you can work with non-minimal coupling, non-minimal derivative coupling, quintessence, even GR, everything put together, just depending on the choice of the coupling functions. So that's why this makes this generalized framework interesting for model, if you want to explore the different types of models. And these are also interesting because there are codes, public codes, which have implemented these Hondeski theories so that you can also see the effects on the CMB and isotropies and do a nice model comparison with the lambda CDM data. Now, just the Jargon's equations here. So you have Friedmann equations and the evolution for the scalar field. And now the evolution in here, the rho phi is actually an effective term which has contributions arising from these non-trivial interactions that you introduce depending on the choice of the functions. There are also certain conditions that need to be kept in mind so that the theory is stable, that is, you avoid gradient or ghost instabilities and to make a consistent setup. So with this, I will introduce this first work, which is done with my collaborator Basundhara Ghosh and my PhD supervisor, Professor Rajiv Kumar Jain. So here we explore Lagrangian, where the dark energy is not a cosmological constant, rather a scalar field which has certain interactions like non-minimal coupling, Galileans, and a canonical kinetic and potential term. What this brings about, so you get an effective energy of state which could actually go to negative regimes at very high redshifts. The dark energy could become negative at high redshifts, as well as it could lead to a phantom type of behavior in the equation of state. So this is a subclass of Hondeski by choosing the different functions. The results are something like that. Here is how the expansion rate of the universe will change with redshift. The black one is the lambda CDM one, and the colored ones are the different for the data. We see that we can get a large value of H0 at z equals to 0 for different choices of model parameters, and a smaller value of the expansion rate falls behind lambda CDM at high redshifts. And what interestingly happens is that the energy density of the scalar field, which is the dark energy, is negative at high redshifts, but it transits to a positive value at present time. However, the total energy density of the universe always remains positive, so there are no pathologies in the theory. And this transition from negative to positive energy is also imprinted as this feature in the equation of state. And the late time dark energy equation of state could be phantom as well to resolve the Hubble tension. For the analysis, we included the data, the low redshift data in the first part, where the BAO cosmic chronometers, Pantheon Plus and SHOES were used, and we got a value of H0 around 71, which elevates the tension a little bit so that with this setup. However, this data did not include the CMB measurements. So this is what was the next work, which is done in collaboration with Ujjwal, who is a PhD student at IISc, and Professor Rajiv. So the motivation here is that how the growth of structures, because now you are working in a modified gravity theory, one has to take care of how the growth of structures at late times also changes, because this could have significant effects in comparison to GR and could help to distinguish the underlying theory of gravity. And the effects on the CMB power spectrum as well are important because you are proposing a model as an alternative to lambda CDM. Then finally, this will help in a combined likelihood analysis to say something about the validity of model in comparison to the standard lambda CDM. For this, we implemented the code in a Boltzmann code and see the CMB and isotropies. Also, the effect on the growth of structures, why it is important, just to illustrate that, for example, the growth rate can be significantly deviating in case of non-GR theories. Here in the quasi-static limit, how the matter perturbations evolve, this equation is given here. The G effective in case of the GR is just a Newtonian constant. However, in a modified gravity theory, this could be a function of time. So that's why there could be significant deviations in the F sigmoid, which are crucial to consider. This is what we, these are the results for the model implemented and seeing the features in the expansion rate and the equation of state. So here the equation of state, again, one can go in the phantom regime or non-phantom regime depending on the choice of the coupling parameters. Similarly, in the growth rate, here the dashed one is what we expect in the lambda CDM picture, and here are the growth rate measurements in the model, which show a suppression, feature of suppression at the very low rate shifts. Finally, you also see what could be the effects of potential effects on the CMB power spectrum. There could be shift in the peak because of the modification of the expansion history. And Finally, we do a data analysis to find the best fit constraints on the parameters. When the data are taken separately, for example, the BAO, the Pantheon Plus, when they are taken separately, we find that model can indeed allow a large value of H0. Similarly, when Planck data alone is taken, the model gives an equivalent fit to the data comparison to lambda CDM model. It also shows a preference of a large value of H0, the blue one, and a smaller value of S8, here the blue one, again for the model, showing that the model has the tendency to resolve the H0 tension. However, in the combined likelihood analysis, when we combine the low redshift and high redshift measurement, this is tightly constrained because of the non-overlapping regions of the parameter space, and we find that the model only leads to an extension to a large value of H0 that is not much of help, which is around 68. However, the interesting properties that the model has, for example, the phantom crossing and the negative energy density, are important in the light of these recent observations like DESI and also JWST, which has seen some high redshift galaxies which are not, which cannot be formed in a lambda CDM picture. So this is the summary that we explored a dynamical dark energy scenario, and this shows interesting features like phantom crossing and negative energy density. However, we do not find that the model statistically outperform the lambda CDM model, but there are certain features which require further exploration. And I will just conclude with this slide that this particular type of, this particular class of non-minimal coupling model actually shows very interesting features because it can naturally give rise to phantom crossing type of features which are seen in the DESI data. And there could be deviations in the growth rate as well because this is a modified gravity theory. There could be scale dependent effect which could be probed with the galaxy LSS data and could help us to probe the deeper nature of dark energy by looking at the effects on the perturbations. So yeah, that's all. Thank you.
I had two questions here, Heshi. One is you talked about stability and speed of sound of the perturbations and so on. But in that particular slide, slide 12 or something, you had you know, the primordial perturbation, the curvature perturbations. But in the context of dark energy, I don't care about that, right? I need to know what happens to something like P by rho or P prime by rho prime at later times.
These could be related to the scalar field perturbations at late times, right?
I will not talk about curvature perturbation at late times. I will talk about what you had later, psi and phi.
Yes, yes.
So you will look at P prime by rho prime, whether it is positive or negative. So this constraint, you can, since later you're considering them generated during inflation, I am sympathetic, but it's not valid, necessary at late times.
I think I have the slide because the first part was on inflation, but what I meant is the sound speed of the scalar perturbations in the late time.
Okay, so I don't know what you do at late times. How do you ensure? Is P prime by rho prime positive at all times?
Yeah, CSS squared should be positive at all times. CSS squared.
Okay, it depends on what is CS squared.
So
that CS squared is different from
for that,
the CS squared I'm talking about.
Delta rho, P by delta rho for the scalar perturbations, that should be ensured to be.
That is not that C squared.
No,
CS
that's what I think here it's for the inflation part because the slides are from the inflation part. What I meant is the perturbation speed for the scalar components be positive all the time.
And in one of your slides, you had a W of phi or something as a function of Z, and there were so many spikes. There one.
Yeah.
Why are these spikes arising?
These spikes are arising because the energy density of the scalar field was negative at high redshift. It transits to a positive value at very low redshifts. So the spike is just an indication of the transit from negative to positive value of the rho of phi, which is the dark energy.
And your speed of sound is well behaved across all of them?
Yes, it is. For this setup, we ensure that it is well behaved, it is positive and real throughout.
Okay, thank you.
No. This is for different choices of the parameters. These are for different, it's showing that where this crossing will happen will depend on the strength of the coupling.
After all that effort, chi squared, delta chi squared is 0.6.
It's 0.6, yes.
Okay.
Yeah. Yes, that's what this Hondeski type of models give you, that the effective equation of state goes to a phantom regime. So instabilities like ghost instability, which will arrive in a simple phantom scenario, could be avoided by adding some effective terms which are arising due to non-trivial interactions of the scalar field with gravity or itself.
You already showed in one of your slides, but you quickly went through it. So what happens to the gene scales as we change our parameter? That how does the matter power spectrum change as we introduce this new modified gravity? So you showed the matter power spectrum already.
Yes. So the matter power spectrum, we saw that there could be some suppression in the power at very small scales. That is what the feature we obtain, and that is attributed to some changes in the G effective, or the Planck mass being an effective Planck mass evolving in a non-minimal coupling theories. So it could be attributed to that.
Okay, thanks.
Any more questions? Okay. I think we are ending this session. When will we be back? 20 minutes. After 20 minutes, we'll be back. Okay. Thank you very much.
So there are two announcements. The bus that is returning from here to Pallavaram or IIT Madras Ginger Hotel will leave at 8:30 instead of 9:30. There were several requests that the dinner will be over by 8:30. And the second thing is that if you arrive late and are yet to collect the registration kits, please contact one of the local organizers. Thank you.
Welcome back to this last and final session of today's program. This is Supratik Pal. I am from ISI Kolkata. I am chairing this session. In this session, we have, I think, 5 or 6 flash talks. So each talk will be 5 plus 1 minute duration. I'll give you a signal after 4 minutes so that you have to finish within 5 minutes. You have to keep time. And then maybe we can take 1 or 2 questions, quick questions for, in order to keep time. Okay. So our first speaker is Hondeski Saha from MIT University.
Good afternoon everyone, I am Hondeski Saha. I have submitted my PhD thesis under guidance of Dr. Surojit Chattopadhyay in the Department of Amity University, Kolkata. In the Department of Mathematics, Amity University, Kolkata, and I am thankful to the scientific organizing committee members here, sir, that I am here to present my work in this prestigious platform. Today my topic of presentation is worm inflation with the most generalized form of holographic dark energy and some particular cases with corrected entropies. Entropic cosmology provides a strong foundation for the lead time acceleration of the universe. The lead time acceleration of the universe is the consequence of the entropy due to the information stored in the universe. So, for an entropic force, the entropic cosmology assumes that the horizon of the universe has an entropy and the temperature as the transfer of the energy in the system. So, we aim to develop a study which generalized Bekenstein-Stephen Hawking entropy in the holographic dark energy formalism. Here we have defined 6 parameter entropy, which is equation 1, and 4 parameter entropy, which is equation 2. The alpha plus minus, beta plus minus and gamma plus minus are the positive constants, and here we have used 4 parameter entropy as it is the it contains lesser quantity of parameters which generalize the entropic Bekenstein-Hawking entropy. And for the HD holographic dark energy formalism, holographic dark energy density is 3 zeta square by L square. L is nothing but the infrared cutoff, and here we have used the 4 parameter entropy in the form of L, where S equals to A by 4G and A is equal to 4 pi R square. Here RH square we have defined by Hubble horizon. To find the Hubble parameter, we have to choose the scale factor. Here we have chosen hybrid form of scale factor, which is the combination of exponential scale factor and the powerless form of scale factor. Exponential form of scale factor defines the later phase of expansion, as well as the powerless form elaborates the early phase of expansion. So, by choosing the scale factor, we can derive the holographic dark energy density, and from the continuity equation of dark matter, pressureless dark matter, rho m dot plus 3h rho m equals to q, where the interaction term q can be chosen as 3h b square rho dm. From the aforementioned equation we can solve, and we get the dark matter density, and by combining both the density, by adding those two density, we can get the holographic dark fluid density in 4 parametric most generalized form of entropic cosmology. And from the second Friedman equation, we can get the pressure, and as well as if we choose the bulk viscous scenario, pi is equal to minus 3 xi h square, we can get the effective pressure. And here we have shown in the figure 1 the US parameter, which is asymptotic in the later phase of the universe, and as well as the effective US parameter, which cannot avoid the Big Rip singularity in the figure 2. And here we have validated the GSL in the figure 3, where S dot is greater than 0, and we have validated the thermal equilibrium, and for S is proportional to A, the area of the horizon, so that's why not the volume of the horizon, so that's why we have shown the corrected entropy, which is logarithmic corrected entropy, and as well as the power law corrected entropy, which shows the which validates the GSL.
Shambhuti, you have half a minute left.
And in the warm inflationary scenario, the inflating field is always dissipates the energy to the thermal radiation bath, and for this dissipation term, Q is very important for us, and for by taking Q is less than 1, we got the slow roll inflation, and in the figure 7 we have shown the slow roll inflation R and NS plot, which is not favorable to the observation 2018 Planck data set, but in the figure 8 we have taken Q is greater than 1, and here we can see for the E folding number 60 to 70, it is favorable to observation. And this is my conclusion, which I have concluded each and every slide previously, and these are my bibliographies, references, and in this work the lots of calculations are done, and half of the work has been published in Nuclear Physics B, and half the warm inflation portion has been we have submitted in the EPJC after revision. And thank you.
Thank you, Shambhuti, for a nice talk. Maybe one or two quick questions. Okay, so I guess there is no question right now, but so you'll be here, you can have discussions later on as well. So let's thank Shambhuti once again for a nice talk, and move on to our next speaker. Our next speaker is Ganga R. Nayar from NITK. Once again, 4 + 1 + 1 minute.
Hi everyone. So magnetic fields are omnipresent. So along with the astrophysical magnetic field, we have some an indirect evidences that there is a cosmic magnetic field. So a well-established theory of the origin of such magnetic fields are not yet there. So we explored the possibility of one such theory, which in which the primordial magnetic fields might have originated. So we study the primordial magnetogenesis in the framework of loop quantum cosmology. So loop quantum cosmology is an attempt to extend the inflationary scenario to the Planck regime using the concepts of loop quantum gravity. In this theory, the singularity is replaced by bounds. So before the time t equal to 0, we have a contracting phase and the universe bounces into an expanding phase. So the singularity is replaced by bounds, and after the bounds there is inflation and the story continues. So in such a regime, in such a framework, The background is governed by the modified Friedmann-Reiser equations, and in this equation here the rho supremum is the maximum energy density of the universe, which the universe attains at t equal to 0. That means at bounds. So when the energy density attains the maximum energy density, that is t equal to 0, the scale factor attains the lowest value, which is 1. So in such a context, the scale factor evolution is given by this, and after some 10 power 6 seconds there is inflation, 10 power 6 Planck seconds there is inflation. So this is the framework which we work on, and in this context we are studying the generation of primordial magnetic fields. So the theory is that there were some tiny quantum fluctuations in the primordial regime, and these fluctuations grew along with the evolution of the universe and are present as the cosmic magnetic fields in the present. So even though we tell that it is not that easy, because even the fluctuations are formed, these fluctuations will not evolve, they will just remain as tiny fluctuations, because the standard electromagnetic action is conformally invariant. So any fluctuations produced would not grow and will not be relevant to us. So the conformal invariance has to be broken, and we break the conformal invariance by introducing a function which is dependent on the scale factor, and we take the idea of Jerome and Yokoyama, and we introduce a function which is proportional to scale factor, and the coupling function has a form a power p, and using such a function the conformal invariance is broken, and this is the modified total action. And in such for such an action, the equation of motion of magnetic vector potential, electromagnetic vector potential is this. Here you can see if this F is absent, this is just a simple harmonic oscillator, and such a solution is not relevant to us. So in with this equation of motion, we have this magnetic potential, electromagnetic vector potential A, and we are interested in studying the energy distribution, and we study the spectral energy distribution using the power spectrum, which is nothing but the distribution of energy density over the logarithmic scales. So we have the electric and magnetic power spectrum given by this equation, and we study this in the LQC context. So again in the equation of motion, we have this term f double prime by f, which is effective potential. The square root of effective potential is plotted here, and we have chosen two forms of coupling function, which is a power 2 and a power minus 3, and the evolution of and the root of effective potential is plotted here. So the modes which are here in this range, these modes see the bounds and they will be affected by the bounds, but the modes here, their bounds is not seen by them, and they will not have any effect, and they will show this law of behavior itself. So this we can see in the power spectrum. So this is the power spectrum in LQC context, and here you can see the power spectrum is largely dependent on depending on the scales. These are highly scale dependent. So the modes which are here, they are enhanced, their amplitude is enhanced due to bounds, but in the Slaughter regime, the power spectrum is largely scale invariant. Also they show a dependence to the form of coupling function. So we summarize that in the LQC context, the power spectrum is largely dependent on the scales in the lower k value, but in the larger k value they are scale independent, and they also have a high dependence on the coupling function. So I thank the organizers for the opportunity. Thank you.
Thank you, Ganga, for referencing in time. Questions, comments, maybe? Yes, Sriram has a question.
Is there an issue of back reaction around the bounds? Because I see the power, there is significant power on very small, very large scales.
We are exploring the possibility. So for -3, there is back reaction.
Even for the other case, if the spectra are like that, there may be a back reaction because of the rise in power. You may want to check.
Yeah, sure.
Any other questions or comments, maybe? If not, I guess not. Okay. So let's thank Ganga once again. Next speaker is Shubhasish Maiti from IIT.
Okay, thank you for this opportunity. My name is Shubhasish Maiti. I mainly talk about the late-time magnetogenesis in presence of ultralight axions and its observational imprint on GW signal. So we already know that our universe is fully magnetized in observable different scales, and there is several ways we can indirectly probe. One of them the CMB anisotropy. It puts the upper limit of the magnetic field around 10 to the minus 9 Gauss, whereas the gamma ray observation actually put the lower limit is around 10 to the minus 18 Gauss. So the question is how this magnetic field are originated. There are several ways of originating this kind of large scale magnetic field. Mostly studies is the inflations, and there is a post-inflationary dynamics. They can also be produced the magnetic field and QCD phase transition, and other there is several ways. Now we always question that whether this magnetic field actually originated in the beginning of the universe, or there is some late time dynamics that can actually enhance that such that we can get such huge magnetic field at CMB scales. So here we consider the dark ages era, because we already know during the dark ages photon are freely travels, and if the ultralight axions are present in the background, they can easily couple with the photons or gauge field, and when the axion field are oscillating in the background, they give you the tachyonic instability in the system, and they can enhance the magnetic fields. So this is the alpha is the some coupling constant, f is the decay constant of the axion fields, and phi is the axions, and the potential of the axion field typically known, and here m phi is the mass of the axions. When these axion field are oscillating, when the mass of the axion and the background Hubble are comparable, then the axion field are oscillating. When they are oscillating in the FLW background, the system of equation look like this, where you can see this the effective omega term is a negative when this entire quantity is negative, and it is only possible when the axion field are oscillating in the background. And then we have a tachyonic instability in the systems. You can see in the this figure we are to plotting the co-moving magnetic field as if I for to this mass 10 to minus 28 electron volts with alpha is equal to 80, and over the time there is a huge enhancement on the background magnetic fields, and it is the corresponding the present observational bound that we can see for this typical mass range. They can generate the magnetic field at 1 omega parsec scale, which are well consistent with the CMB as well as the gamma ray observations. So as there is a huge amount of production of magnetic field during these times, obviously they can produce significant gravitational background during these times. So obviously this is a well known equations. This is the source by the electromagnetic field during this era. Okay, so if we solve the equation numerically, they typically proportional to the b to the 4 well known, and you can see that with this mass range in the CMB's length scale, CMB observational length scale, they can produce the significant gravitational wave with the multiple peaks, and in this type of magnetic scenario actually generate the helical magnetic fields. So obviously we should expect the gravitational wave that produce, they are also be helical in nature. So in future CMB observations, if we detect the B mode polarization, then they can be probed as well the magnetogenesis scenario and can be constrained the mass of the axion if they are present during these times. So this is actually mainly the outcome of my talk. So yes, the ultralight axions with a mass 10 to minus 31 to 10 to minus 27 electron volts with the coupling strength with this 17 to 80, then they can generate the huge amount of magnetic field at CMB scales. This is one of the alternative way of generating the large scale magnetic field obviously, and obviously they can generate the significant gravitational wave background, and maybe they can be detected by B mode polarization in futures. So this is, I think, the outcome of my talk, and thank you for that.
Thank you so much for finishing very in time.
Yeah.
Okay, so maybe we have 1.5 minutes for questions and comments.
You think of producing an ALP field by breaking one additional U1 symmetry in the early universe. That's how you propose this kind of coupling. So how will the spectrum of the electric or the magnetic field in this scenario depend on the energy scale where the additional U1 symmetry is broken to produce the ALP? The spectrum today strongly depends on the Hubble scale during inflation.
Yes,
The
yes.
question I'm asking is that how will the spectrum or the strength today will depend on the scale where you break the additional U1 symmetry to produce the ALP.
It is very actually late, I think. The mass is very small. So
during what epoch are you breaking the U1 to produce the ALP?
I think electroweak symmetry breaking this low mass you can.
Sriram has some questions.
What I'm asking is related to what Rajiv is asking. When are the magnetic fields produced?
During dark ages, actually they are again excited because of the
Dark ages means you're talking about, below redshift of 1000.
Yes, yes.
They are generated on large scales at that time.
Yes, because of the background axion, that if this low mass axion are oscillating.
But what are the initial conditions on the electromagnetic fields?
Yeah, they can be generated from these inflationary fluctuations. Even if we consider they have some power law, k to the power 3 power law.
Oh, you are assuming something at early times which is evolving now.
Yes, yes, yes. They are already presented some amount, but this strength is very low because they are
amplified at this time.
We are amplified at later time.
So did axion decay into magnetic field?
Axion kinetic energy converted to the magnetic field kind of.
So axion field is decaying into magnetic field, is that?
Yeah, kind.
Any other questions? So, Suvasis, just a small question. I mean, because you want it to rather enhance during the dark ages, so do you need to do any kind of fine tuning for that? Because
no, I think we don't need to do any fine tuning. The mass is very important. Like obviously there is a particular mass range they are oscillating during dark ages. This is the fine tuning parameters, and alpha is the free parameter. You can choose accordingly.
I guess. Okay. Okay, so let's thank Suvasis once again. Next speaker is Debarun Pal from ISI.
Okay, first of all, thanks to the organizer for this opportunity. So today I will be discussing about how primordial gravitational background can act as a complementary probe of the dark matter annihilation. And this talk is based on this work. So the dark matter. So we all know that 26% of our universe is dominated by this kind of matter. Although there are several cosmological and astrophysical evidences there. But still now we are not very clear about this particle constituent. So to understand it, there are several phenomenological models over there, and out of them weakly interacting massive particles are the most promising one. And on top of that, to satisfy the relic abundance for the present day dark matter, the thermal cross section should have this specific value, and which is also a WIMP miracle. So till now this WIMP scenario working very well and very smoothly until and unless it faces some challenges by the indirect detections, which puts some stringent upper bound on the thermal cross section at the lower mass scale. So the question is, how can you revive from this situation, or these WIMPs, how can these WIMPs can satisfy the relic then? Now this specific value of this thermal cross section is possible if we assume the dark matter freezes out during a radiation domination background. So if anyhow the thermal histories get modified during the time of the freeze out, then this scenario may be resolved. So that is why in our work we have considered an early matter domination phase before the onset of the BBN, and we have assumed that this matter domination is occurred due to some domination of some long-lived massive particles. So obviously this domination temperature and the decay temperature strongly depends upon the mass and the decay rate of these massive particles. So now in presence of this early matter domination phase, the dark matter satisfies the relic if this quantity becomes unitive. Okay. So, this quantity, because here this decay temperature is related with the EMD parameter space, and this cross section and this freeze out temperature is related with the dark matter parameter space, which clearly relates between the relation between the EMD parameters and the dark matter parameter space. And this figure reflects the same. By tuning this EMD parameter, this whole parameter space can satisfy this relic. So, the question is, how can we probe this whole phenomenological structure? So, here the gravitational wave background comes into play. So, the primordial gravitational wave background can probe this early universe cosmology, and from there we can extract out the information of the dark matter, and this builds the basic framework of our work. The dark matter parameter space can be directly probed by the indirect detections. On the other way around, this parameter space can be probed by the GW experiments, and hence there is a complementarity between these two type of experiments, GW experiments and the indirect detections. So, in our work we have considered this primordial gravitational waves generates during the quantum fluctuation at the time of inflation, and this is the gravitational spectrum. So, at the left hand side represents the variation with respect to the EMD parameters, while the right hand side is the variation due to the dark matter parameter space. So, now you can find the GW spectrum passes through a number of GW, the GW spectrum passes through a number of GW detectors. So, that is why we proceed to properly assess the detectional process, and that is why we have performed the signal to noise ratio analysis for the BBO, ET, LISA and the Mureris, and you can find this whole set of parameter region is greater than the means the signal to noise ratio is quite high. This is lies within the great means we can detectability is quite high. At the same time, since this is the era of the precision cosmology, we also perform the 1 minute left. We also perform the Fisher forecast analysis to estimate the uncertainties on the dark matter parameter space while it is probed by the future GW detectors. Okay. So, here at the end we have projected both the future reaches of the indirect detection searches and the GW detection searches, where you can find the overlapping region between these two type of experimental setups. Okay. Now, once we find this overlapping region, we further proceed to perform the Fisher forecast analysis. For an instant, this region, in this region, ET can probe this gravitation, this dark matter parameter space with the 1% uncertainty. So, that is why this overlapping region reflects the complementarity between these two searches, between these two types of searches, gravitational wave and the indirect detection. So, here in this diagram we have described that the indirect detection is made by the gamma ray searches, and here we have made the same analysis for the neutron detectors. And at the end I end up my slides by stating that the primordial gravitational wave background provides a novel opportunity to probe the dark matter, and also this links between the cosmological searches by considering the early universe cosmology with the traditional indirect searches. Thank you.
Thank you, Devarun. Quick questions? Maybe. Yes, please.
Can you go to the slide containing the spectral energy density of gravitational waves?
Yeah.
So, what exactly is happening? Why is that rising there?
Oh, so yeah, in this figure we have considered a blue tilted spectrum. So
primordial spectrum.
Primordial spectrum is blue tilted. We also consider.
What is the level of the tilt?
What
NT is
0.5. NT is 0.5. Both the diagrams.
Okay, because during the matter dominated era it will come down.
Yeah, so that is the come down, and also since there is some blue tilted spectrum, that's why it's not tilted over.
All right, thank you.
Any other questions or comments? If not, let's thank Devarun once again, and let's move on to the next speaker, who is Rosna K from NITK.
So, very good evening to one and all. So, this talk is based on a recent work where we have done a phenomenological investigation of the two anomalies present, namely power suppression and lensing anomaly. So CMB anomalies are basically signature which depart from the predictions of the nearly standard scale invariant model, and the two anomalies which I will address is suppression of power at large angular scales and lensing anomaly. So studying these anomalies are important because these may be the signals of physics which are beyond our standard lambda CDM. So this is the suppression of power which I am talking about. Like for low multiples, there is significant deviations from the predictions of the standard lambda CDM model, and this is the plot in the angular space. So in order to quantify the suppression of power which is observed at lower multiples, we have a quantity known as S half, and the value of S half observed by Planck is 1209, which is very much less than that of the predicted value by the lambda CDM model. And next anomaly is lensing anomaly. So the CMB photons which are traveling from the last scattering surface get weakly lensed because of the presence of the large scale structures, and the effect of lensing can be seen in the higher multiples as the smoothing of peaks. So WMAP team has introduced a parameter known as AL in order to check the consistency between the effect of smoothing observed at the larger angular scale, effect of smoothing observed at larger multiples, as well as with the effect of smoothing which can be derived from the lensing potential. So the Planck basically reports the value of AL to be greater than 1, which is more than 2 sigma away. So my aim is to investigate whether there is any primordial connection between these two anomalies, one where the effect can be seen at lower multiples and other where the effect can be seen at larger multiples. So we have basically used some phenomenological models, some extensions to our standard NSATs, that is SA plus beta model and SA plus alpha plus beta model, and the important property is these models are agnostic about power suppression. So this is the S half value which is tabulated. What you can see is for the model SA plus alpha plus beta, the value of S half observed is much less than that seen in SA model, and since the value of S half is low, we can say that power suppression is most in the SA plus alpha plus beta model. So we have tried whether there is, investigated whether there is interconnection between these two anomalies, and what we have observed is in method 1 where we have analyzed or where we have constrained the value of AL using varying all model parameters, and in second method where we have fixed the value of alpha and beta to the marginalized mean value, what we have obtained is in both cases there is elevation of lensing anomaly, because as you can see the value of AL is closer to 1 in method 2, and in method 1 there is a slight increase of error bar which in turn lead to an elevation of lensing anomaly. So we have analyzed our significance of our models using AAC and BAC criterion, and we have calculated a term delta, which is the difference between the model which we consider with that of reference model, and what we have found is delta BAC, if you check, that indicates basically the data prefers a strong model, but here we have analyzed our result using the whole multiples. But if we concentrate on lower multiples, when we check only the local feature, since the power suppression is only a local feature, we need to restrict the data only to lower multiple cases. Then what we have observed is the value from the delta BAC, the SA plus beta and SA plus alpha plus beta models are favored. So we have also done an analysis using TR4 data with updated likelihoods. So this is the value of S half plotted and the departure of lensing parameter from 1. So in lensing anomaly, as can be seen, significantly reduced with the Hilly-Pop combination, even for the case of SA. And I want to stress the point that higher the amount of power suppression means lower the S half value, more consistent is the value of lensing parameter from 1. So we have investigated the ability of future CMB missions in constraining our models. So we have used ICO, CMB Bharat, as ICO have improved the polarization sensitivity much more than the Planck. We expect more tighter constraints on our model parameters, and for that we have done we have assumed two fiducial cosmology, like in one with without suppression and one with suppression, and what we have obtained is the value of alpha and beta constrained are such that it rules out the null values by more than 4 sigma. So this is the summary. Thank you.
Thank you, Rashna, once again for finishing time. Questions? Sovik.
Hi, I just don't understand why you didn't use the high multiple polarization data.
Yeah, I have used it, I have used
No,
it.
but you wrote just temperature, then low L and low E.
No, I have done with that also. See here.
That is for this one, but for lensing anomaly, you only show.
No, we have analyzed our result using even for polarization. I didn't show that here.
Okay.
Yes.
So how are you using those AIC and BIC in this? Like, can you just go to that slide and...
This one, right? Yeah.
Yeah, so you have chi-square, you have delta AIC, delta BIC, and now...
Because from this judgment criteria I have analyzed.
Yeah, that's okay, but how are you using it? Like, are you filtering out some models based on this, or?
Yeah, we from this delta BIC we have analyzed that if we consider the whole data sets like from L equal to 2 to 2500, what we observe is basically delta BIC favors favors standard NSATS model, but we strongly believe that the power suppression which is seen is only at lower multiples. So hence we need to analyze only for the lower multiple data. Then we can say that delta BIC is strongly favoring SA plus beta model since it falls in this criteria, and it have a moderate preference for SA plus alpha plus beta model. This slightly increase of delta BIC is basically due to the increase of this new parameter beta.
Okay, so I'll discuss with you later because
sure,
I want to use.
Okay.
Okay, so maybe we can continue this discussion later on, as you said. So let's thank Krishna once again. And our next speaker is Saurabh Pal from ISI Kolkata.
Okay, good afternoon everyone. Today I will be discussing about exploring massive neutrino signature in galaxy bispectrum multipole and its detectability aspects in Euclid. This work is mainly done in collaboration with Devanjan Sarkar, Ikmo Samartha and Professor Supratik Pal. So here is a brief outline of my talk. First I will discuss about the impact of massive neutrino in power spectrum as well as bispectrum, basically in matter power spectrum. And as we know that, and then I will discuss about the galaxy bispectrum multipoles and whether the effects of neutrino mass and galaxy bias in the galaxy bispectrum multipoles, and analyze the galaxy bispectrum multipoles in a spherical harmonics basis and try to observe whether, try to explain whether Euclid can detect this nucleus signature in these multipoles. So, okay, first of all, why going beyond power spectrum? And that is already previously discussed in previous session that to extract information for power spectrum for higher k, we need to go to higher loop corrections, but in the bispectrum we can get information in the tree level where there is mode mixing. So in that sense, another thing that you can also break degeneracies between cosmological parameter like F sigma 8 and also galaxy bias and neutrino masses. So first let me discuss about the impact of massive neutrinos. This is the primary equation that I have only shown one, the Euler equation, the effective Euler equation of the neutrino fluid, where the neutrino has a sound speed, and then we can define a corresponding free streaming length associated with the sound speed. Because of this, in linear theory, neutrino basically suppresses the matter power spectrum and bispectrum by this amount, 8 f nu and 13 f nu, where f nu is the neutrino mass fraction, and this is well established. Now here we want to go to the higher order correction to the this Euler equation and the continuity equations. So we define the Ricci space bispectrum in Fourier space by this Fourier average of the delta 2, delta 1 and delta 1. Okay. So the bispectrum is defined in terms of K1, mu and T. And the two-level bispectrum can be written like this, where F2 and G2 is the higher order kernel here. But these kernel are now neutrino corrected. Okay. So in this spherical harmonic, in this using this coordinate system, we can break this two-level bispectrum in higher in multiples and define the corresponding reduced bispectrum multiple as well. So here we analyzed the various multiples 0, 0 to 4 higher order multiples as well, where this is basically allowed by the triangular inequality, where the bispectrums are we can get the signature, and this is basically the squeezed limit, and this is stressed limit, and this is equilateral limit. As you can see that in the squeezed and in the linear limit, linear triangle configuration, the neutrino signature are most prominent. And we also further checked whether this can be detected in Euclid-like galaxy survey, and for that we define a covariance matrix, okay, and between two multiples Lm and L prime L1 prime. And for any realistic survey, we need to include the finger of God effect as well as the short noise, and we do include all of them. And we define the signal to noise ratio by this, the signal difference between the bispectrum also in presence and absence of neutrinos. And we obtained that in the stressed limit configuration, neutrinos we can detect with the neutrino signature with greater than 5 SNR in both 0, 0 and 2, 0 multiples. And this is also true. However, in 2, 1 and 2, 2 multiples, these signatures are strongest in the linear and squeezed limits. And once again, we can also detect this signature in 4, 0 and 4, 1 multiples as well, but that needs to assess to more smaller scales, and that our theory doesn't allow, because that we have to go to the higher order correction for the bispectrum all loop corrected. So in summary, basically we saw that neutrino corrected bispectrum multiples, there in real space there is a negligible effect, less than 0.1%. That's why we analyzed the redshift space enhancement, and we obtained that it has a 1 to 2% effect for neutrino mass 0.12 electron volt, and various multiple moments can be detected with greater than 1 sigma, greater than 1 SNR for Euclid-like galaxy survey. So that's all. Thank you.
Okay, thank you, Saurabh. Yes, questions? Okay. Or go.
So when you do the calculations, are you looking at the full matter power spectrum and bispectrum, or are you looking at the CDM part only of the matter power spectrum and bispectrum?
No, we're not looking at the matter bispectrum, first of all. We're looking actually the galaxy power spectrum.
Right, so that is only the CDM part.
Right,
so
CDM plus
that
baryon
suppression part is actually not 8 F nu in the power spectrum, that's 6 F nu. So
that
that should be
That is basically, this suppression is basically the total matter power spectrum suppression. This is not CDM only.
Any other questions? Yes.
Yeah, in your multiple movement plots, I saw there are some white spots. Yeah, later when you were showing. Yeah. Why it look distorted? Because
It's actually shown for greater than 1 SNR only.
Oh, okay. Okay, so the white part is not detectable. Okay, fine. Yeah.
Any other questions, comments? Okay, so let's thank Saurabh once again and move on to the next speaker, Shubhra Mandal from University. Shubhra, right? Shubhra Mandal from University of Bardwan.
Good afternoon. I am Subramandal from University of Burdwan. I am going to talk about our present work on the dynamics of cosmological phase transition of Bose-Einstein condensate dark matter in Thales cosmological framework. So we all know that standard cosmology explains many things, but it has some tensions like missing satellite problems, core cast problem, and edge problems. So Bose-Einstein condensate, what it does, that it introduces some quantum pressure and it can fix that small scale issues, and that Thales entropy, this generalizes thermodynamics for gravity for long range interactions, and from this we can explain the age of the universe and the acceleration of the universe without considering dark energy. So our goal is to consider both of the frameworks and merging it and study the evolution of the dark matter from its normal to Bose-Einstein condensate state. So start with the Boltzmann-Gibbs entropy. We know that it is good for short range interactions and independent systems, but it fails for long range interactions like gravity. So here some consequences are, we get divergent partition functions and that entropy energy relations inconsistencies for gravity. So we require some other theory, and for that we consider that Thales cosmology. Thus Thales cosmology emerges from Thales entropy. It is a non-additive in nature, and it can explain gravity, and from this we can explain the acceleration of the universe without considering dark energy. We consider dark matter as boson particles. So it may possible that whenever that universe cools down to certain temperature, it can form Bose-Einstein condensate, and it can be governed by Gross-Pitofsky-Parsons equations. And before that condensation, it acts like a normal dark matter and follows linear equation of state. And after that, that equation of state is like it quadratically depends on density. So when it forms BEC condensate, we consider that is a first order phase transition, because some of the mean field theories suggested that it is a first order phase transition, and for that we keep that pressure and temperature fixed during the first order phase transition and calculate that temperature, critical rate shifts, scale factor, and some other quantities. So for a typical value of mass of dark matter 0.55 eV and scattering length of order 10 to the power minus 10 centimeter, that critical redshift comes 1200, and the time corresponding to it is 10 to the power 11 seconds. So these are the typical values. We don't have that data analysis. So we keep some constant that that it cannot go beyond 6 eV, because beyond 6 less than 6 eV can form BEC condensate for any temperature in cosmological framework. So we define a quantity condensate fraction and shows how it evolves with time, and from that we can find that the total time duration to form a condensate, and it is about 4.3 into 10 to the power 12 second for a typical value of the Thales parameter 0.35. And we calculate the deceleration parameter. We can see that deceleration parameter is solely dependent on the Thales parameter beta, and for beta less than half, we can see that Q Q takes the negative value, so we can explain the accelerated universe without considering any dark energy. So these are some plots that how that condensate factor grows, and that grows with time for different Salis parameter value, and that distillation parameter varies with beta, and other two graphs are that Hubble parameter, how it changes with time for different beta values during condensation and after condensation. So now we can fix that age problem also. We know that in matter dominated universe, that age of the universe is predicted is below 9 gigayear, but if we consider Salis cosmology, it can alleviate the time of nearly 1.65 times. So it can, it can solve that age problem of the universe, and there is no discrepancy remains, and this we can do without considering dark energy. So this has been published in this article, so you can see. Thank you.
Thank you, Subhra. Any questions? Okay, so let's thank Subhra once again and move on to the next speaker, Arun Chakraborty from IIT Guwahati.
Pointer. Okay, so I think I'm audible. Good afternoon, everyone. At first, I want to thank the organizers for giving me this opportunity to present my work in this platform. So today I'll be talking about generalizing the Bogoliubov versus Boltzmann approaches in gravitational production. Okay, so this is the overview of my presentation. At first, I'll tell you the main motivation of this study, then I'll very briefly touch upon these given points, and I'll tell you the main result, and finally I'll conclude my talk giving a brief overview to the main outcome of this study. Okay, so let us start with the motivation. To study the gravitational production of mass level massive scalar spectrum of all the scales from large to small scales, and when I say the scales, I mean to say actually the different k modes of the scalar fluctuations, the different Fourier modes of the fluctuations, and we have studied this production process during inflation and the post-inflationary general radiating background in the Bogoliubov framework. This is a well-known framework to study the quantum mechanical particle production in the time-dependent background. And our another objective is to study the finite mass effect of the IR spectrum, and in this attempt we compute a specific IR scale, and below which all the long wavelength modes of the IR scales will be affected by the finite mass effect, and their associated spectrum will obviously deviate from its massless limit. And finally, our goal is to compare the prediction of the two approaches, that means these Bogoliubov and Boltzmann approaches. Different gravity mediated processes like two inflatons are scattered into two scalar particles, suppose, and this process happens through the graviton exchange, where this H mu is the graviton field, and this is the well-known gravitational production process which is quite extensively studied in various recent literature in the Boltzmann framework. So now in this work, one of our main motivations is to study whether these processes are equivalent to the small scalar UV spectrum generation that is studied in the Bogoliubov treatment, by taking into account the small scale inflaton oscillations into account for any general radiating background. Okay, so these are three main motivations of this study. So now I shall quickly show you the main spectral behavior of this work, then I will tell you the main result. So this is the large scale spectral behavior of the spectrum and solving the Mukhanov-Sasaki equation. Anyway, I have not shown that equation here. Finally, we reach these expressions. So this is computed in the Bogoliubov treatment. So left panel is showing the massless IR spectrum behavior. So this is omega phi is the rating equation of state, and 2 nu bar plus 3 is the spectral index, which actually varies from -6 to -3 for the equation of state, which varies from 0 to 1. and the light panel is actually showing the finite mass effect, and where this Km by Ke, this is the ratio as I was talking about earlier. This is this specific scale below which all the higher scales will be deviated from its massless limit. So these are the specific form of the scales. For omega phi equal to 1/3, this is behaving like this, and for other than 1/3 equation of state, this is behaving like this. Both are the function of this mass, and subject to this specific scale, we finally have this massive spectral behavior. I mean the large scale spectral behavior in these two regimes. For the sub-Hubble case, this is behaving like 1 by k cube, and for the super Hubble mass, there will be an exponential suppression effect, and in additionally there is some spectral behavior. Anyway, I have not shown that complicated factor, and m chi is the Bayer mass effect, Bayer mass of the scalar field. Sorry. So now I will show you the UV spectral behavior in these three different equation of state regime. So this is one of our interesting results. We have analytically computed these results in three different equation of state regimes. So in less than 1/9 equation of state, this is another interesting findings, analytical findings of our study. Why this particular equation of state, there is a sudden behavioral change of the spectrum. So below this regime, there is a spectral behavior, dominant spectral behavior, which is a function of omega phi, and above that 1/9 there is a constant dominant behavior of the spectrum, which is independent of the Breathing equation of state. And additionally, there are two coefficients, n0 bar and n0 bar, which anyway carrying the information of the background oscillations, and they gives rise to the generation of the interference term, which will anyway explain the small scale oscillation of the spectrum that we shall see soon. And this psi is some phases which has been also associated with these terms, and this is psi is also function of the scale and the background oscillation term. So now I will tell you the Boltzmann spectrum. So this is the interaction Lagrangian, okay. So where h mu is the field which is coupled to the stress energy tensor of these two fields, and this is the associated Feynman diagram, and subject to this specific interaction, we finally end up having these two spectral behaviors in the Boltzmann treatment by solving the Boltzmann, well-known Boltzmann equation, and these two behaviors for 1/3, one is for omega phi equal to 1/3 and another is for other than 1/3 equation of state. So these are the specific spectral behavior in these two approaches. So now I will show you the important results of this work. So these two plots are actually showing the spectral behavior in all the scales, that means large and small scale, and you can clearly see in the large scale regime in both the plots for two equation of state 0 and half, with the increase of mass the spectral behavior gradually depart from its massless limit and they start becoming flat. And interestingly, we see that the heavier the mass, the earlier the flattening happens in the momentum space. If we look towards from right to left, the earlier thing will happen, and this is quite consistent with the turning point equation that we analytically computed earlier. That means the scale Km by K end. Okay, so another, and this is true for both the equation of state. Another interesting behavior that is in the small scale regime, and we see that both the approaches, that means Boltzmann and Bogoliubov, predict more or less the similar spectral behavior in this small scale regime, and this indeed establishes the interesting equivalence of these two approaches, and this is independent of any general rating equation of state. And another interesting point is that analytically computed interference term can nicely explain the origin of the small scale oscillation in the UV, I mean the small scale oscillation or the UV regime oscillation. Okay, so these are the interesting characteristics of these two plots. And finally, I will come to the key findings of this study. We have found that this IR spectral index varies from -6 to 3 for this equation of state regime, and these two different mass regimes, one is for sub-Hubble and super Hubble regime, one will experience the exponential suppression effect and another will follow the flat behavior, and this is the UV scale behavior. And finally, we can say there is an interesting equivalence of these two approaches, which is independent of any rating equation of state. So this is one of the important findings of this study. Okay, so thank you
for a nice talk. Questions? Yes.
What is KE?
Okay, so K is the scale which left the horizon at the inflation end. Okay, where? Yeah. So this is the scale which left the horizon at the inflation end.
Okay.
Okay.
I don't see any other raising hands, so let's thank once again.
Thank you, everyone.
And last and final speaker of today is Ujjwal Kumar Upadhyay from IISc.
thanks to the organizers for giving me this opportunity to talk about my work. I'm a PhD student at ISC and Raman Research Institute. I'll be talking about peculiar velocity correction in cosmological inference from supernovae data. So you know that our universe is very well described by this 6-parameter lambda CDM model with the underlying theory of gravity as the general relativity and the energy content of the universe distributed among dark matter, dark energy and the ordinary periodic matter. Further, with the assumption of homogeneity and isotropy, the space-time of the universe is described by this FLRW metric, where AT is the scale factor and its logarithmic derivative is the Hubble parameter. So we have 6 free parameters. In order to constrain all of these parameters, we need to have information about the evolution of background as well as perturbation in the universe. However, some of these parameters can also be constrained using background data only. So the supernova data is among the best probe for this background expansion. In the supernova data, we have magnitude and the redshift. So magnitude is computed from the observed flux and redshift from the spectral analysis. So this is what we have in the data. Now these magnitude and redshift are related by this expression. So theoretically we can compute magnitude at a given redshift by this relation, where dl is the luminosity distance which depends on the redshift, and that is given by a given cosmology. So given a cosmology, we have different parameters. Depending on the value of these parameters, we will get this m, and we can compare the cosmological model with this data and constrain these parameters. However, the presence of peculiar velocity affects the inference of these cosmological parameters. So peculiar velocity is the velocity of galaxy or any object relative to the Hubble flow. So suppose this is the Milky Way galaxy, and we are targeting at some supernova residing in this galaxy. Then this galaxy has a velocity, recession velocity, due to which it is going away from us, that is due to Hubble flow. But in addition to this Hubble flow, it can also have some velocity or peculiar velocity due to the attraction of some other galaxies. Further, so if this is the case, then the total observed velocity will be different from the cosmological expansion. So this can arise from, this peculiar velocity can arise from different sources, like due to our motion relative to the cosmic rest frame, or due to the motion of the galaxy inside the galaxy cluster, or due to the motion of the whole cluster towards some bigger structure. So if this is the case, if there is some peculiar velocity, then our observed redshift will have contribution from cosmological as well as this peculiar motion. And in observation, we cannot disentangle these two effects. And what enters in this expression for this magnitude is only the cosmological expansion. So if we use this observed redshift and we do not take this into account, then it will bias our result. So in this case, we see that we have now errors in 2 variables. We can treat this as errors. We have errors in both variables, redshift as well as in the magnitude. So we can treat this as an errors in variables model. So errors in variables models are just model fitting problems with errors in both dependent and independent variables, something like this. In such cases, even for a very simple linear model, there is no analytic solution. And for non-linear model, it is not obvious how to write the merit function. For simple cases of non-linear models, when the model is smooth, continuous and differentiable function of its parameters, we can invert that function and we can write the likelihood. But in general, there is no method for fitting such such models with errors in both variables. So our approach, so first we define our approach, we come with an approach to consider this errors in variables problem, then we apply it to cosmology. So suppose this is our model, y as a function of theta and x, where x is independent variable, theta is the cosmological parameters or any parameters, model parameter. In that case, this is how we write the usual likelihood. But if we have errors in both variables, what we do, we treat the independent variables also as parameter. So we replace this x by x star. Now x star is a parameter, and theta is the model parameters plus this independent variable parameter x star. Now the total number of parameters become more than the total number of data points. So in order to avoid possible model fitting, we include this regularization factor p chi square, which is given by this expression. So this is the expression for chi square distribution in chi y square. And this chi y square, the general chi y square is given by this expression. Here px, this is prior on x star, and p theta is prior on the model parameters. Now, based on that, we write this is the likelihood. So, I have just taken the log of that expression for the redshift magnitude relation, and this is the regularization term. When we take log, this is what we get, and this is the usual chi-square term. We also, to compare with other estimators like even, which is the general estimator for model fitting, which does not take into account the z error or the redshift error of peculiar velocity. And this is another case when it takes into account the peculiar velocity, but only for the linear approximation of the model. So, we linearize this model redshift magnitude relation, and then we use this method. So, now this is the result for the 3 different cases. For even E2 and E3 shown in different colors, we see that we get a slight shift in the central value of the parameters, inferred cosmological parameters, omega matter and H naught. And this is a table showing the same value. So, in even case, when we completely ignore the effect of peculiar velocity, we get 0.28 and we get 0.30 in case of our estimator, and this is in between, that is the linear approximation. And this is for the Pantheon data and the lambda CD model. The interesting thing is there is no model or measurement of peculiar velocity involved. So, there is a background model for the cosmology, but no model for the evaluation of peculiar velocity. So, we see that there is a few % shift in the central value, but still all these values are consistent with each other. Now, we applied it to the simulated data with different sigma m. So, at present, this is the value of sigma m, that the uncertainty in the magnitude in this supernova data. Now, we take a smaller value with more precise data, we see that there is more significant deviation in these. So, we expect that in future we will be able to distinguish or to capture this effect of peculiar velocity in cosmological inference. So, this is the summary slide. The effect of unaccounted for peculiar motion is to shift the estimate of cosmological parameters, and to take this into account, we consider cosmological model fitting as an errors in variable problem, and for this problem we treat the independent variable as parameters, and with Pantheon data we see a few % shift in the cosmological parameter, and it also allows us to estimate the peculiar velocity of individual galaxies. So, currently we are working on it, and up to a lower rate, depending on the precision of the data, at lower redshift we can actually estimate this peculiar velocity of individual galaxy. Thank you.
Okay, thank you Ujjwal for a nice talk. Rishi, maybe.
Yeah, so you chose one regularization scheme to avoid overfitting.
Yes.
But so is your result sensitive to what kind of regularization scheme you choose, or is this the only regularization possible, or other regularizations are possible, and will the results change if you choose something different?
Okay. So, you can take other regularization also, and okay, so this is one choice of regularization. We can also take other regularization. The simplest should be, so the role of this regularization is to impose a chi-square distribution on this chi-y square. Now, we can just take this chi-square, we can impose that chi-square per degree of freedom remains close to 1. That would be even simpler case. And the effect, so we can take different kind of this regularization term. The effect of this is to keep chi-square closer to 1, but it does not affect the result very much. But yes, it shifts to slightly better fit.
So, here this chi-y is a free parameter?
Chi-y square is given by this expression, just yi minus f theta.
Okay. And the k is a free parameter?
K is the number of degrees of freedom. So, in this case, I have taken this total number of supernova minus number of model parameters theta.
Yes.
Can you explain what do you do with the error bars on Z? There will be error bars associated with redshift also.
Yes. So, in case of this peculiar velocity, we do not have error bars in Z because the spectroscopic measurement gives very small error, and but if we have some errors on redshift, this our method will take that into account already. It will go as in prior on theta on these redshift parameters.
Okay. Any other questions? So, how much is the improvement in error in adding peculiar velocity?
This chi-square you are asking? The improvement is around 0.05 or something.
in chi-square. But that does not matter. Even if I do not include this, we'll get roughly the same result. But yes, it does move in. And it also depends on the precision of the data. So if you have better precision, it can improve it.
If you include the errors in redshift measurement as you were suggesting, do you expect an improvement in chi-square or what?
No, actually, if we include this, that will be basically restricting a prior that it is in this line. But we have, so I do not expect much change in the result.
You are forcing chi-square to be 1, right?
Yes, yes.
Right. That's what I expect. Okay.
So as long as the result is dominated by the data, the priors will not affect it.
Which part of the data is telling you about the peculiar velocity?
Actually, okay, so in the redshift range, you are saying.
So even if I give you a sample, how are you disentangling between the peculiar velocity component and the galaxy's true component? I mean, how do you must have an estimate, right? Which part of the information is telling you to distinguish that?
Okay, basically, okay, the information is coming from the model. So you are assuming a background cosmological model that is telling you what should be the value of correct redshift. So basically, so when you do not have redshift or errors, okay, then you can estimate these parameters H0 and all these. Okay, now you want to also estimate the redshift parameters. So that also can be done if you have very precise data. So in the magnitude error, you move in the up and down direction to fit it better. Now in the redshift error, you move in the horizontal direction. So that
maybe
is
my question is the following, that the peculiar velocity is so non-linear, particularly in our local universe, it's very difficult to make it a cosmology model dependent statement. In fact, if you see the
cosmological model for peculiar velocity. Yes, exactly, and that is why our result is very interesting, because it does not assume any peculiar model for peculiar velocity. The evolution of peculiar velocity, it is coming from just the lambda CDM background model plus the supernova data.
I see. Thanks.
Any other questions, comments? So we are done. Let's thank Ujjwal, and in fact, let's thank all the speakers of all sessions today. And maybe over to you, Dheeraj. Well done.